welcome everybody to the afternoon sessions. If you could quiet down and take your seats, please. All right, starting out this afternoon's discussions, we have Wenbo Gu doing Open Sage, next generation of agentic AI. Over to you.
Okay, cool. Nice to meet everyone. I'm Wenbo. I'm currently assistant professor at UC Santa Barbara, also a research scientist at Meta MSL. Today, I will talk about our recent work, OpenSage, which is a new agent framework where we think could be the future of agentic AI. Before we talk about OpenSage, let's look at the current agent world, how people build agent, right? So basically, the idea is like there's pre-specified agent structure, agent topology, and also tool size, memory structure before you build agent. It's kind of like you build a software, you know exactly what you want to build. You have a clear kind of like system design, and then we build the agent, and then we let the agent run the job. But if we dive in and think about the kind of like limitation of this paradigm, the problem is like if we do pre-specified topology, and also we pre-specify the set of tools that kind of constrain the generalizability of the agent a lot, because reason is we want agent to do complex long horizon job, but sometimes the agent may spawn its own sub-agent along the way of execution. Along the way of execution, agent may find out, oh, the set of tools I have is not enough. I need to invent or need to be added for more tools to finish more complex jobs. But if everything is pre-specified, it can constrain the agent capability or generalizability a lot. So that's kind of motivate us to design OpenSage, which we think is what we call Agent 2.0. Pre-hands is like Agent 1.0. So basically, it's similar as we designed the machine learning models. If we think about it like 10 years ago or even like 20 years ago, when we design machine learning models, the first step we're gonna do is feature engineering. Right, so we need to think about given raw data, what are the features we use, how to extract feature sets from the model, from the raw inputs, and then there are so many feature engineering methods. That's kind of adding our human knowledge, or what we call inductive bias, into the model. But then people found out, we don't need that step. You just train the deep neural network model on the raw data. The model will figure out by itself. And actually, there, without the inductive bias constrain the search space of the model can actually, search for better like solutions in a larger kind of search space. So that's kind of here we think about similar. What if we don't build an agent? What if we don't do all those kind of like manual feature engineering, like pre-specified workflow, topology, tool size? What about we just build a minimal set of scaffold that enable the agent to build its own agent, right? For example, we enable some initial tools for the agent, so the agent along the way, agent can spawn its own sub-agent, design its own workflow, topology, write its own tools, or even write its own memories. So that's kind of like the idea behind OpenSage, is to really unleash the power of AI when building agents. Basically, we want something like AI build AI, agent build agents. To do that, sorry, it's not working. Sorry, the clicker is not working. Okay, now it's back. So as you can see, what we want is we want to provide the minimal set of scaffolding that enable agent to build its own agent, including write its own topology, workflow, write its own tools, and also design its own memory. So for the sake of time, I skip the technical detail. Basically, we redesigned the whole, ADK, what we call agent design cookie, to be, that's bad, that's good, to be able to enable the agent to kind of explore its own topology, write its own tools along with the way of execution. So here's a comparison between our OpenSage with Google, OpenAI, all those frontier agent developer kits on this new capabilities, as we can say, that's why we call OpenSage, that's Agent 2.0. That's really the kind of like next generation of agent construction framework that enable all these capabilities, freedom, flexibilities that existing, non-existing ADK is able to offer. And then let's look at the performance. So here we meaning kind of test OpenSage on coding and also cybersecurity related benchmarks. This is our performance compared to Cloud Code and also Codex by the time of we release OpenSage. That was about like February this year. As you can see on all this existing benchmark, like notable benchmark like CyberGym, Terminal Bench, SwiftBench Pro, and DevOps Stream, OpenSage was able to outperform all existing agent frameworks. This number are a little bit outdated. OpenSage is still evolving. We are also kind of seeing new performance on these benchmarks as well. And another kind of recent trial we feel very exciting is we actually run OpenSage on the real-world CTF game. For those who know about it, we run it against the DEF CON 2026 qualification game that's kind of considered Olympic in the world of offensive security. It's the most challenging security kind of competition. All there typically require a team of professional hacker working on 48 hours, like even sometimes there's a team with hundreds of hackers work on all these challenges, try to solve them. What we do is like we try OpenSage on 15 of the non-interactive challenges because actually will not be, the organization kind of doesn't allow AI to solve the challenge and submit. So what we do is we run in parallel at the same time the challenge release. So in total, kind of 15 challenges, we're able to solve 7 of them. And after we do a post hoc analysis, 4 of them actually was very close. If we gave, I don't know, another hour, we can solve 4 more challenges. Basically, in total, we were able to retrieve 8 flags and put us on the top 5 in all the teams that ever participated in the game. One statistic I didn't wrote here, also very interesting, is OpenSage was able to beat all the team that claim they don't use AI or use low AI. Basically, this is the AI-only agent that's able to beat a team of professional hacker that didn't use AI in their competition. So basically, this shows OpenSage was really able to solve real-world challenging tasks because actually all these kind of competitions, all these challenges, when we look at the trace, OpenSage took like 5 or 6 hours of continuous runs, spawn like thousands of sub-agents to solve them. So basically demonstrate OpenSage was really able to scale up its own topology and is able to solve challenging tasks. Now what we are doing is like not only the agent, because we know like building agent is the first step, but the brain, the model itself also very important. Sometimes model need to co-evolve with the agent. This is also kind of motivated by our observation in the sense it's like if we say run OpenSage with the latest model, we found that actually the model haven't fully figured out how to build its own agent. Sometimes model want to spawn new agent, but it actually fail. So this motivates us to bring up this kind of end-to-end or more like holistic framework where we think about we need to build new agents to train the model. We need to basically train the model to better spawn its own agent, better write its own tools. And also we think about the inference stack, like the trajectory of agentic trajectory is actually very different from pure QA task. We also are trying to develop new agent inference frameworks. But overall, what I want to deliver is like we envision the future of AI agents is really, the future of AI agents is really try to open up the freedom to let AI do more explorations in terms of everything that eventually build up to the agent. What we want is to provide meaningful scaffolding, provide a powerful model, provide a more efficient inference framework to make that happen. Okay, thanks.
All right, Next, we have Ramesh Raskar, professor MIT, on the Agentic Web and the Bizarre Era of AI.
Hello, everyone. How's it going? All right. Fantastic. So for some time, we have been in the factory era of AI, where some large companies would produce these products in large quantities, and we would just consume them. But very soon, thanks to edge AI and small models and things running on the edge, things running on your own machines, we're shifting to the bazaar era. So a lot of our work at MIT is about thinking about when we'll have billions, maybe trillions of AI agents on the open web. What would the internet of AI agents would look like? And to motivate that, imagine a scenario where Sarah in Texas, in rural Texas, has a health condition. She goes to her Dr. John and says, hey, I have chest pain, I have comorbidity, and she's just not getting a good answer from her doctors. And Dr. John can go on the open hive, on the open web, and say, hey, listen, for $100, can somebody solve the problem for Sarah? And when that happens, billions of agents all over the world wake up. And they say, hey, maybe I can take a piece of this $100, and they can look at the data, if it's related to corresponding health condition, start training models, also create a coalition, start collaborating with each other, and eventually maybe a handful of them can solve the problem for Dr. John. And those, let's say about 10 of them solved together, those 10 get paid out from that $100, and everybody else kind of disappears. And then eventually Dr. John gets an Expedia-like answer of how he could help Sarah, the patient. And so what's happening here is it's not like agents for e-commerce, right? This is commerce that's possible because of AI agents. And Dr. John is not accessing some kind of an amazing health model, AI model out there, but he's tapping into a network of intelligence. And that network is available as a marketplace, right? This is what we mean by the Internet of AI agents and the commerce for agents. So again, we are kind of in the mainframe era of AI, kind of a factory era of AI, but very quickly we're shifting to the PC era. Some companies are already using agents within trusted boundaries, the intranet of agents, but very soon we'll shift to the internet of agents, where agents are collaborating and negotiating with other agents that are well outside the trusted boundaries. But that's still just for geeks, how we can connect. That's like the internet. To go from the internet to the World Wide Web, we needed HTML and browsers and URLs and all the good stuff. And Project Nanda, that originally started at MIT, stands for Networked AI Agents in Decentralized Architecture, right? A mouthful. Nanda for short means Sanskrit, means joy in Sanskrit, but also name of my sister. All right. So what does it mean to have billions of agents out there? And if you take this example I showed you of commerce that agents will conduct, I think the closest analogy I can imagine is high-speed trading, high-frequency trading. And the reason why high-frequency trading works is we have a bunch of things, right? We have, there is a registry, there is, every merchant, every stock, is pre-qualified. There is somewhat price transparency in how that works. There is a way to deal with fraud detection and so on. And all these things also had to be built for the Internet of AI agents, right? So this is a massive infrastructure that's going to come get built for the billions of agents that are out there. So anybody here like an OpenClaw fan here, right? But OpenClaw is great, but it's only inbound. It only behaves as a tool. I cannot call your OpenClaw agent. It's like having a telephone that can only make calls outside, but can never receive calls, right? So it's a one-way agent, not a bidirectional agent. So the question is, who's going to build this infrastructure? But a more problematic way to think about this is whoever builds this infrastructure will also own it. So the question for us is, will we end up in a walled gardens of this Internet of AI agents, or will we get an open and vibrant and neutral and safe and scalable web for AI agents? So that's the mission for us, for Nanda. And we think that there are 4 main bottlenecks. And if you can solve those 4 bottlenecks, there's a chance we can keep the agentic web as open as today's internet, as opposed to how we see on the mobile phones like iOS and Android or Facebook and Twitter, all the walled gardens. So the 4 bottlenecks are a ICANN DNS-like structure. Second is passports and certification. Third is obvious, which is interoperability. And fourth is attestation. So I'll go through this very quickly. And our group at MIT has been working in this space for last 11 or 12 years. So we've been on this journey of thinking about what happens after AlexNet when we have billions of individual AI systems that are interacting with each other. And now, going forward, we think there are 3 main research problems we need to solve. Originally starting at MIT, but now we have many collaborators. The first one, as I said, is like the DNS for agents. The second is knowledge pricing. We think it's very critical that data, models, inference, compute, all needs to be priced. Just the way when you hire a candidate, we can figure out their salary. And the same way, we have to do knowledge pricing. It's a very beautiful mathematical problem. Come talk to us. And the other problem is co-learning. The last 14 years have been a fantastic progress in machine learning, but going forward, we think it's all about machine co-learning, about how 2 agents learn from each other. And when you think about co-learning, it's not just about, agents buying services and transacting, but they're going to form coalitions, they're going to negotiate, they're going to compete, for resources, and they have to achieve decisions. And there'll be some alliances, there'll be some betrayal. It'll be like the Game of Thrones among agents. So the other thing we need to do is we need to have a starting point for the web. There was something called Yahoo. Those of us as old as me, and Yahoo kind of created a safe space to explore what the web is. And we need something similar to do that. So we created something called Nanda Town. So go check out Nanda Town off of MIT website. So it's kind of a sandbox that allows anybody to bring enterprise agents, payments, memory. If you're working on any of these spaces, you can come to Nanda Town and explore this extremely heterogeneous system. And you can have some ethical hackers there and so on as well. It's moving very, very quickly. So I encourage you to explore Nanda Town. And then the research, of course, works in multiple directions. Agentic devices, this knowledge pricing, co-learning, new forms of Asian marketplaces, and so on. And of course, this is happening under a very large tent that involves large companies and startups and governments and so on. And more recently, we have this series of hackathons called Nanda Hack that are sponsored by different organizations. So just go to nandahack.media.mit.edu to explore it. Now, when we talk about billions of agents, we should be thinking about at nation scales. So what's happening now is, thanks to a lot of work at Nanda Town, we're able to work with very large ecosystems. So for example, in India, we launched something called Doot, which means messenger, and 1.5 billion agents that are not owned by, there's no corporate capture, and that run on the identity and payment rails they already have. City of Boston is also launching with us, a Boston agent initiative, and I invite you to come and talk to us about how the civic agents are evolving as well. And what you'll quickly realize is that today we're thinking about agents for X, agents for coding, agents for browsing, agents for debugging, agents for shopping, and so on. But we need to flip that and start thinking about services for agents, X for agents, infrastructure for agents, compute for agents, insurance for agent, healthcare for agents, education for agents. Everything that we do in the society needs to be done for agents, right? So I think the open agentic commerce is going to emerge because intelligence will be discovered, intelligence will be priced, and intelligence will be coordinated at scale. So come join us at nanda.mit.edu. Thank you.
Next, we're introducing Shiva, Principal Applied Scientist, Amazon Web Services, towards adaptive agent frameworks.
Good afternoon, everyone. My name is Shiva Kashishnathan. I'm a Principal Applied Scientist at AWS. Me and my team are working on developing AI agents for monitoring and observability for large-scale cloud operations. And today in this talk, I'm going to share some broad research directions that we've been exploring to make agents more adaptive. So I think, let me start with, today's agents are already pretty capable, right? So we all know that how good they are good at planning, tool execution, retrieving information, iterating over the solutions to solve complex tasks, right? But as these agents get deployed in more mission-critical applications, we in AWS believe there are some critical research questions that need to be solved because they can be widely deployed. And here are some of them that we have been exploring in our team. The first question that we've been exploring is this question of how should agent allocate computational resources, right? Imagine that you have a fixed computational budget and you want agents to best utilize that computational budget to solve the problem at hand. The second question is along making agents reason better, right? So agents needs to be able to explore multiple reasoning paths to make decisions in a more efficient fashion. And the third research question that we've been exploring is the question of how do you evolve agents over time, right? So the agents are not static pieces, but that's continually adapt over time to make and learn how to solve the tasks over time better. So in this talk, I'm going to just focus on the first two tasks, but I'll just briefly end up with how we are looking at the third problem at the end. So let me start with the direction one. So this is the notion of budget-aware adaptive execution, right? So today, if you look at most agents, they have a fixed execution policy that you define using a prompt or some other local heuristic, right? I guess what our goal is to make these agents learn these execution policies. So the agents can learn over time these execution policies so that and then they decide how these policies are then executed. And then you also have notion of a computational budget. You want the agents to work best under some computational budget, right? So abstractly, you can think of this as a problem where you have some context. The agent has some context. And it is to decide the best next action to do. The action could be retrieve information, use a tool, verify the results, update memory, whatever. There is some action space. And the important constraint is that there is notion of budget, right? So there is a budget that the agent has, and it has to respect that budget while executing these tools, right? So again, if you think of this a little bit more, I think this can be phrased as in terms of a formulation, we can be phrases as a constrained Markov decision process. And we've been using this framework to learn these policies, right? So again, the goal is to maximize some kind of expected utility under some notion of subject to some computational budget, right? Again, the budget could come from latency, cost, token, or whatever you want to think of, some notion of budget. Right, and does it work? And yeah, the answer is yeah. We've been had some success in implementing this. So what we've been showed that this plot, on the plot on the right-hand side, shows these adaptive agents learning better execution policy than using a scale rise reward model, which is commonly used in practice, right? On the other plot on my left side is showing that it's also more sample efficient, right? So you're reaching the same competence using fewer iterations. So the amount of samples you need to get to some level of competence is significantly lower if you use these kind of adaptive execution policies, if you learn these adaptive execution policies. Okay, the second direction that I would just briefly want to talk about is notion of parallel reasoning, right? So today we have these agents, or at least these models, which are following a single reasoning path, right? And we have been exploring ideas that allow models to explore multiple reasoning paths in parallel. So these parallel paths are kind of learned during training and not during inference time. And then they are coordinated to select one path, right? So the answer is one. So there is some coordinated reasoning that happens at the end, which takes these multiple reasoning paths and produces one answer. And again, we have been implementing these ideas and testing it on benchmarks, and both over mathematical reasoning and coding benchmarks, we have been getting consistently good results. These are some results on some maths and coding tasks, and you can see the results for pass 1 to pass k. We have been getting better than very strong baselines. And especially the results are impressive on k equal to 1, which is like the first when anyone gets just one result out. Okay, so I'm almost out of time, so I just want to finish by going back to the research questions that I was interested in. So we have been, I just mentioned about this budget-aware adaptive execution, where the goal is to learn an execution policy that's adaptive and best uses the constraints it has. And then the second question of parallel reasoning, where you're trying to generate agents to have multiple reasoning, so that multiple reasoning paths, so that they explore multiple paths to solving the same problem. The third question that we have also been focusing is this notion of continual model or agent adaptation. Again, the goal is to come up with principal post-training schemes that can adapt to new tasks. The main challenge there is to make sure that when you learn the new task, you don't forget what you learned previously, right? And we believe that these kind of solving these kind of three research directions will help us to generate the next generation frontier agents. Thank you.
And next we have Tanya Rusta joining us virtually. She's Director of AI AMD, a Berkeley alumni, speaking on information retrieval in the age of agentic AI.
Hi, everyone. I'm Tanya Rusta, and I work at AMD as the Director of AI. Sorry I wasn't able to make it in person, but I'm glad at least we have Zoom. I will be spending the next few minutes discussing evaluation framework for agentic IR. So let's start with the shift. Basically, what has happened in the last few years is that we have moved from traditional information retrieval, classic RAG, where you had this straight line of there is a query from the user, the search engine would get the documents, come up with a ranked list, re-rank it, and then present the list to the user. To this more of an agentic flow where the agent actually does planning, tries to figure out what the intent of the query is, does the search, gathers results, analyzes, critiques, and then presents the final result. So this means that the unit of work has basically has moved from lookup to an ongoing conversation with the world. And this agentic IR shows up in the deep research agents, as most of you have seen with ChatGPT and other agents, that you're able to put a question out. For example, here's the question is about cholesterol medication, and the agent basically tries to understand what the intent of the question is. Then it goes and uses various tools to gather the websites, different information, price information, drug interactions, etc., and then comes up with the answer, tries to ground the answer into retrieved evidence, and then finally presents the results to the user. And this basically saves us many, many hours and having to kind of go through all the document, blog posts, etc., and trying to figure all of this out on our own. And a lot of times this kind of agentic IR is now taking over potentially 20 turns. So it has become a multi-hop thing. But here's the uncomfortable gap that still sort of exists. And that is that when we want to kind of evaluate these agentic IR, we still tend to look at the final answer, use scores like Blue and Rouge to see if the final answer is correct. And given now the information seeking is really interactive, multi-turn, it has this temporal aspect, it has to be evidence-driven, simply grading the final answer doesn't work very well. So what do? We basically have to look at the trace and start to, try to assess the correctness, of every hop. Was it adequate to answer the user, the cost in terms of number of tokens, latency, etc. And in terms of where the field is heading, I would say there is the reasoning aware retrieval. So now not only you have the keywords from the query, you're looking at the agent's reasoning traces. There is the multi-turn hop-aware benchmarks that are being developed, like MTRAG. There is the retrieval, graph RAG, so that you can look at the relationships. There is self-RAG to cut through some of the hallucinations, and adaptive RAG to basically route queries based on their complexity and effort. And finally, actually looking at the number of tokens that are used, and optimizing around that as a metric for information retrieval. So what I want to leave you with is that, our information seeking has changed. The agents have changed how we get information. And that means that we have to also change the way we assess if these agents are doing the right thing and if they're achieving the goal that they have set out. And that's all I have. Thanks for having me.
Thank you, Tanya. And next we have Denis Akirov, Senior Staff AI Scientist with ServiceNow, speaking on our small LLMs ready for coding agents.
Hi, everyone. So actually, this is a bit of a personal story. So a few months ago, I was flying transatlantic and realized that as AI scientist, I can be very inefficient without a coding agent while disconnected from internet. So I realized that maybe I should develop my own local coding agent and see if a local LLM running on my MacBook can actually handle realistic coding agentic tasks. There is a link to this repo. So I just open sourced it recently, and you can also see the presentation there. This agent is called Ask Me, and it does one small thing at a time. So it's basically designed around three key ideas: how to minimize the context that we pass to a small LLM, because LLMs are not really good when you pass them a lot of context for small language models running locally. And the second is that we do very small actions at a time and immediately verify that action. And the third thing is we minimize the reasoning as much as possible. Only use it on recovery loops when things go wrong. So here is an example. You give a small LLM. So in this example, it's Qwen 3.6. And basically, you want to just create a small program. Think of a hello world, compile it, and run it. But the thing fails because actually it compiled it into a temporary directory, but it needs to execute from another directory. So things like this are much harder for small LLMs to realize. So we have to make very, very small changes and verify them one at a time. So around this idea, we basically develop a loop. So Ask Me is a very minimal loop. It's just one file. It used to be 1,000 lines of code. Now it's like close to 2K lines of code. And basically you want to minimize number of big planning steps you take, smaller steps, and only go back when things go wrong. So I evaluated this on a few hundred tests, and here, this is just smoke tests with two families of LLMs, Gemma 4 and Qwen. And basically, it works except one Qwen model. This was just a sanity check that we can use it. And then next is actually running realistic tasks. So this is actually building features for an app And what I realized is that basically these agents can do most of the work, but the issue is that they fail to verify their work and have this full loop, observe what happens, go back and solve it. So basically it passes most of the tests, but not all tests for developing an app. And it's the same story across both Qwen 3.6 and Gemma 4. And for the record, this was run on open router, not locally, because locally it will take me ages to run this. And there is a limited memory on my MacBook. Next, I think basically this wasn't an example, just creating a small agent running locally with minimal harness. And it shows that it can basically work locally with a very small LLM, doesn't need a large code base like Codex or Cloud Code. Yeah, you can look at results and how it works in this repo. I guess I also want to give some shout out. So I actually compared it against Pi harness, which is the most minimal harness that people use at the moment. It's much more efficient than Codex or Cloud Code. And I also did some comparison with OpenHands. And basically, this is even smaller than both those harnesses for working with very, very small LLMs locally. So, and it's still a work in progress. There is still like a lot of issues. But yeah, I'm happy to receive any feedback, any questions you have. Thank you.
And now we have Professor Nilu here from UC Berkeley on agentic or agent reasoning requiring compressing information into executable reasoning structure.
Thank you. My name is Nilu. I'm co-founder and CEO of a company called Across AI. I'm also a professor here. What I'm going to talk about today is that basically the whole problem that we're all solving and have been solving for years now is compressing information. Because at the end of the day, that is what a model does. That is what a harness does. We are finding different ways to take lots and lots of information and compress it into a format that is executable. Like a transformer model is executable and predicts the next token. Now, over the next few years, what's going to happen is we're going to come up with more and more architectures that are able to do this in more complicated ways. And one of the first problems that we're going to have to solve is what are the various types of processes and what is the optimal architecture or harness for each of these processes. I want to share one that we've had a lot of success with, which is reasoning graphs. A reasoning graph is a graph of agents. So each of the circles that you see in this graph is one of the agents. And we've identified that for particular processes, especially processes that need to be run repeatedly and with very high consistency, this is a very good architecture to do that. So the way this works is that at the very bottom layer, you have a layer of agents that just connect to all of the different systems where the raw data lives. And all these agents do is understand that raw data. Then you have another layer. These are the layers of agents that do the reasoning. And then finally, there's a layer of agents that take the right action at the right time. So any path that goes from the bottom all the way to the top is one possible reasoning path. And we've seen different flavors of the same idea come up today. Like you could run these in parallel. You could optimize them in certain kinds of ways. Now the question then becomes, how do you create one of these? And we've seen also this idea show up in a couple other talks today as well. And it has to be that it's done by an agent. So what we're going to see more and more is these sort of handshakes between an agent and a harness. And that agent is trained to know very well how to work with that harness. And these different architectures are going to be good at different kinds of processes. So one that we've been working a lot on is this architect agent that works with processes that run consistently and highly accurately, like financial processes or supply chain or something that a company needs to keep running over and over is non-deterministic, still needs to be intelligent, but needs to be highly consistent and explainable. So what you get is very high consistency. We've hit routinely above 95% accuracy in running these processes in examples or benchmarks where even Fable can only hit about 40 to 70% accuracy. And we also get very high speed. No custom code is being written in any part of generation of this harness. It's all the architect agent working together with this particular harness. So we can launch new use cases in a matter of weeks. And the most important part of this architecture is the compounding intelligence and the weights of that model. So every time the architect takes a new use case and creates a reasoning graph for it and learns how to do that, it gets better at doing that. So this kind of a model we're going to see more and more, and we're going to see it for different kinds of processes. I wanted to give you one example of a process that we agentified using this architecture, and that's invoice matching. So very, very large companies receive lots and lots of invoices, and they have to make a very simple decision: pay it or don't pay it. They receive a certain amount of fraud, so they can't pay everything. They also can't sit on it too long, because if they don't pay an invoice in time, it affects the rest of their supply chain. So imagine large companies are processing millions of these invoices every month. So an invoice is received, it has to be matched to a PO, it has to be normalized. There are lots and lots of exceptions, like the units might be different, the currency might be different, there's tax in certain areas. One example that I stuck in my head, which I thought was very funny, is that if it's liquid, it's okay if the amount on the invoice is up to 5% less than what was on the purchase order, but only during summers, because some of it evaporates and there's nothing you can do. So the agent has to keep learning. It's not a one-time, one-shot learning thing. It's also not something that happens just in one session. It's something that lasts, a process that lasts long horizons, months and weeks, and every time you see an exception, you have to learn from it. A baseline agent harness, even using Fable here, only gets about 40% of it right. This is what the reasoning graph that we built, where our architect agent built for this process, looks like. It's made up of lots of agents, their wiring, their instructions, what models each agent should use. Each has their own long-term memory. So all of these decisions, all of these engineering decisions are made by the agent. And what we hit was 99.9% accuracy on this real data example. The first graph was up and running in a week. And in 96% of the cases, not only did we give the right decision, but we were able to correctly explain why that decision was made. This brought down the cost of processing these invoices at this one Fortune 500 from $5 an invoice to $1.50 in this example. And more recently, this week, we got it down to 10 cents per invoice. So those are the kinds of advances that you can make if you are able to take that learning and compress it into a reusable structure. Thank you.
All right, and now we have Johan Schuyler-Smith, Senior Staff Engineer for Temporal, speaking on systems foundations for Agentic AI.
Hi, everyone. I'm Johan Schuyler-Smith. I'm at Temporal Technologies, and today I'm going to be talking a bit about our perspective on the agentic AI landscape and introducing Temporal as well. So just by show of hands, who here is familiar with Temporal, maybe has heard of it? Okay, we've got a few. How many people have actually used Temporal? All right, well, I'll tell you, this is going to be a high-level overview. If you stay past this session, we're also going to be doing a workshop where you can get hands-on and get into the code. So let's just get into it, and let's talk about systems. So when we talk about systems, we're talking about creating some sort of functionality by putting together a whole bunch of components. And in the case of AI, there are a lot of these components. And so we need to get that functionality, but in addition to the core basic functionality, there are these sort of cross-cutting concerns, right? Things like reliability, which Temporal has really a deep experience in. Efficiency, security, evolvability, that includes the scalability, it includes the ability to do upgrades and so forth. Let's dive in a little bit on reliability, because this is really sort of explains the core mechanisms underlying Temporal. So suppose we have an agent. In this case, it's a customer service agent that's going to be helping with returns. And so this agent needs to connect to a whole bunch of different systems, right? Knowledge bases, inventory, ERP. It needs to handle payments. It needs to probably have escalations. It needs to be able to send emails. And in order to make all of this work reliably, what do we need to do? We need to put retries in a whole bunch of different places. We probably need queuing to handle load. We need state management to keep track of the process all the way through. And these are all places where things can go sideways. And so whoever's building this needs to account for that one way or another. Now, traditionally, software interleaves the application concerns, the business logic, with the systems concerns, things like reliability and the other systems concerns that we've talked about. Now, fundamentally, if there's one thing to take away from this talk about what temporal makes possible, is it's this model of durable execution. And what that does is it allows you to write code that puts the system logic over on one side and the application concerns on another, and really isolate that out. Now, the temporal open source project itself, what it lets you do is it lets you build crash-proof applications. It's open source license, so MIT license, and you can back it with a number of different databases like Postgres or Cassandra. There's also a cloud product, but the key thing about it is that it lets you write regular code, regular programming languages, right? Python, TypeScript, you name it. And get crash-proof execution. So how do you recover after a crash? Well, there's basically two ways to get that state back. You can either save it or you can recompute it. And with temporal, you can think of it, and we'll get more of this in the workshop, but simple annotations that you could put on the code, and you could say, here's what I want you to recompute, here's where I want you to save state, okay? And then that's sort of, if there's a trick, that's the trick. There's other cool things like distributed systems from ordinary language primitives. This is pretty cool. But I want to talk for a minute about how companies out there, our users, our customers, are using temporal. This is Venkat, VP of Application Infrastructure at OpenAI. And so one application that's notable is ChatGPT Images, where there's a whole series of steps that need to happen. They need to all happen reliably in order to spit out that image. That was one of the notable use cases for temporal at OpenAI. Codecs on the web is another one, but really there's a whole slew of things ranging from the infrastructure control planes to the data connectors. That's effectively, think about that as building and maintaining the RAG indexes and so forth. And then finally, traditional business processes. And really across the ecosystem, whether it's at NVIDIA or at Cursor, now SpaceX, or Lovable Replit, temporal is being used really across that stack to enable agentic AI. So now I want to dive in and just make a few observations about really sharing how we think about it and what we've learned from working with companies across the ecosystem. So we have this functionality that we need to provide, right? It's an agent, and that means different things to different people. Definitely in a business context, it's basically some system that gets something done, right? And what we spend a lot of time thinking about, particularly in the AI Foundations team, which is the team that I'm on, is really what are the right abstractions, what are the trade-offs that come along with this agentic AI workload? How do we slice them? Which ones do we pick a point in the space? Where do we maybe give you a knob for it? And so just a few observations about these workloads that I think are particularly interesting. I'm not going to read through all of this, but just on the LLMs, right? So this is also, I'll just say, it's a different workload from other workloads we've needed to deal with before in systems. And so it's really fun to be able to sort of rethink these abstractions. So non-determinism, right? So that means that you call into an LLM, you're going to need to validate and store those responses. But it's also interesting because it has this flip side where it's also sort of fuzzy and it's actually forgiving with respect to its inputs. That's the sort of other side of the coin from its outputs not being necessarily 100% determined. Security, this is interesting from the threats side. So you often think about adversarial inputs, things like prompt injection and alignment, but also a great threat model when you're thinking about agents is actually just bad judgment, right? Because it happens, that RM-RF. And so that's driving a lot of our, by accident, right? Not thinking, that's driving a lot of our design considerations. And then certainly from the execution profile, the fact that you're interacting with a world, that's a place where you want to capture your state. You want to make sure that you're there, writing things down carefully. and also bursty load, which calls for serverless, and so forth. Now, another observation that we've made from working with companies throughout the ecosystem is that there's really this spectrum of agency, and that the right solution for a particular application, for a particular functionality, could come from anywhere across the spectrum. And actually, the more agency you have, it's not always a better thing. So when people think about agents, oftentimes they're thinking about this sort of level 3, which is an agentic loop. The LLM makes all of the decisions about what happens next. But if you go over to the left, you look at level 1, there's actually a huge number of applications, something like summarization or so forth, where their job actually gets done really well by having regular code drive the control flow and having those LLMs inserted at very specific points, right? It can be very reliable, and if that gets the job done, then that's probably the right solution. On the other end of the spectrum, we go as far as self-evolving agents, which we now see in some of the harnesses. And so there's a reason for that, but you can also think that's probably not also the right solution for the job. And when we think about abstractions, at Temporal, abstractions for agentic AI, we're really thinking about being able to allow you to dial that in and to, frankly, go back and forth along this spectrum without rewriting your entire application. And so one thing that we are sharing today is the Temporal Agent Harness. So this is not yet a supported product, but if you go and you start the GitHub repo, then hopefully it will be soon. I'll put up a QR code in a second to that as well. But this is a set of abstractions built on top of Temporal's core durable execution abstractions that make it easy to build practical agents for things that, whatever it is that you want to build. So we give you that ability to plug in the inner harness, which could be a coding agent like OpenCode. It could be something like OpenAI Agents SDK, which also has a lot of interesting sandboxing functionality, Pydantic AI, any of these. We've really worked hard to embrace this ecosystem. You can plug your tools, and again, this is really designed to give you abstractions to mix and match. Well, that means you want to talk to it through Slack, through Teams, you name it. So this is just a quick screen grab of what was an open code session. I was in there just fixing a bug in a simple program. And because I've run that with the agent harness, not only am I getting the durability, the reliability if I wanted to run this at scale, but I also get sort of for free, but frankly it's part of the package. I get the observability, the ability to dive in and see what was the agent reasoning about, at the various steps, what were the tool calls and human approvals and so forth that happened along the way. And that's the benefit that you get from really being thoughtful about the abstractions that you're bringing into to your agentic AI. So with that, I'm finished here. I welcome you to stay in this room for the next session, which is going to be a workshop where we're going to get hands-on with Temporal. Thank you.
Hey everyone, how's everybody doing? Everyone doing good? I know we've all been sitting around for a while listening to a bunch of very exciting AI lectures, so I wanna do things a little bit different and put a little energy into this room. If you all could please stand up with me, please, and participate in my small little fun game. I promise nobody will be hurt. So, everyone, thank you so much for getting up. All I want you to do is to find two people, give them a high five, look them in the eye, and tell them you're freaking amazing. You all are amazing. There you go. Love the smiles on the face. Yes, look at that. Continued. Love it. That's it. Thank you guys so much. And one more thing for social media. I'm going to do a little selfie video with all of us. When I say go, just all do something crazy. Go. Woo! That was so lame. We got to try that again. Can you guys like 5x that, please? Ready? Go. Look at that. That was an A effort. Love that. Hey everyone, my name is Nikolai Velatkin. I am a staff developer advocate at Temporal. I am also a dog dad and a roller skater. There's a little preview of my cute little baby, Mia. She's a COVID baby. So today, we're doing a workshop. So this will be hands-on. So if you got a laptop and you want to do a little coding and playing around, that's going to be awesome, because this is, ultimately, I love workshops where you guys can actually leave with some value, doing something, learning something. The best way to learn anything is actually to be hands-on and not just passive listening. You'll retain way more information. But my goal is to cover 4 topics. We probably won't get to all of them. It's a lot of information, but it's okay, because afterwards I'll give you the GitHub repo and you can pursue it on your own should you decide to. We'll do foundations of agentic AI systems. We'll build one. Then we'll build with an agentic framework, which is OpenAI Agents SDK. We'll do a human in the loop, and then we will orchestrate micro agents. These will be multiple agents talking to each other. All of them are going to be via durable, which is what using temporal, which is exactly what Johan just talked about, will actually make it work in real time together. So, what is an agentic loop? Well, an LLM, right? An LLM can reason about context that we provided. What an LLM lacks is the ability to take action whenever it doesn't have enough information. And so an agentic loop ultimately provides an LLM the capability to take action outside of itself should it need other information. And so what we can see here is we can start an agentic loop with some instructions and goals. You can define some information from it. For example, you're a travel assistant, find a flight to Miami, ask for confirmation before booking your payments. With that context, we pass that information to the decision maker, which is the LLM that will start the agentic loop. The LLM will decide, does it have enough information? Or do I need to call a tool? And if I don't need any of that, do I already have enough information in order to provide a final answer? If it doesn't have enough information, it's going to call a tool. Tools are what we define and tell the LLM to use, right? I'm sure many of you all have used Codex, Claude. You'll see it calling different kinds of tools. Those tools are defined by the harnesses. Sometimes they're defined by you. You provide the tools, tell to the LLM that they exist. The LLM will decide when to use those tools. Now, using those tools, it'll decide, it'll get an output, and then it'll decide, does that output give me enough to give you a final answer? Or do I need to continue in this loop of gathering more information until I can comfortably provide an answer? And that is ultimately the agentic loop. There's simpler versions of it. There are more complicated versions of it. Ultimately, you define it. Before we actually jump into building one ourselves, I'm very curious if you would all just scan that with your phone, and you can answer it, whether you know temporal or not. I'm just super curious of the layout of the audience here. It will allow me to tailor the workshop better to fit your needs. I hope most of you at least have heard about it because I'm here on stage. No, I'm joking, but cool. This is kind of like what we've experienced so far. Yeah, and feel free to drop emojis as well. The flying emojis are super cute. Oh, cool. All right. You guys mostly have not heard about it or heard about it but never used it. Okay, beautiful. So this workshop will be very advanced for a lot of you all that have never used it, but I will do my best to walk you through it. And like I said, you'll have the code afterwards to enjoy. Okay, so Johan mentioned this a little bit, but ultimately, temporal allows you to write code as though failures don't exist. What that means is you're going to focus on the business logic of your agents, of your distributed systems. Agents are distributed systems, right? Whatever you want to do, you put that in a workflow, which is what we call it, a sequence of steps that we want to execute, and then you pull out your non-deterministic steps, your API calls, your LLM calls, your database queries. into what we call activities. When you wrap those activities inside of our SDKs, we support all the most popular SDKs, Python, TypeScript, Java, Go, Ruby, and so on. When you wrap those activities inside of our SDKs, we create a history of all of the activities that have been performed up to a certain point. Whenever any kind of failure occurs, we pause at that point in history, and we will wait for that failure to be resolved, which can be seconds, it can be minutes, it can be years. When that failure is resolved, we proceed with the rest of your operations as though a failure never happened. What's even cooler is that waiting for us to proceed with those operations actually doesn't cost you any resources because we've recorded that all in our history. And so this is kind of what interacting with an LLM can look like. You'll see the workflow. The workflow is what we will wrap our entire process under, right? That will involve ultimately calling the LLM, starting that LLM process, invoking it, and then proceeding with whatever steps we need. In our very simplest case, it's just going to be asking it a question. In more complicated cases, when we do human in the loop, it'll involve asking it a question, waiting for user feedback, and going through the entire human in the loop sequence. And so all of that is wrapped in what we call a workflow. The non-deterministic pieces we wrap in activities. These are the parts that can fail. You want that inside of temporal because we will make sure that those pieces never fail. By the way, temporal has 6 nines of reliability. And so in our entire workflow, what can fail? So many things can fail, right? Calls to the LLM due to network reliability. Actually, this morning, I got a 429 being rate limited by OpenAI. API calls can fail, rate limits, services go down, AWS goes down. All of those being wrapped in an activity will allow temporal to pick up from the failures after they are resolved. All right, cool. Less talk and more coding. So let's give our first demo a try. What you will want to do is navigate to that URL, please. On your computer. This is not for phone because you'll be doing a little bit of coding. Less coding, but you'll be doing a lot of interactivity. Navigate to that URL. It will take you to an instruct environment, which is basically a virtual lab, no setup required, and there's a bunch of exercises, and I will walk you through a bunch of them step by step, and along the way, we will learn some things. Everybody has that link? Yeah? Anybody not at the link yet that wants to be at the link? Anybody not at the link yet that wants to be? Okay, I'll wait, hold on for a moment. Ultimately, yeah, I think there might be a form, just enter your information, and then it'll start booting up a workshop. It should be max 90 seconds for the boot. So proceed, click the start button, wait for the 90 seconds. I'll show you what the screen should look like afterwards. It's in a Docker container, so 90 seconds is almost as fast as we could make it. Everybody at the right place? Anybody not at this URL yet? Beautiful. Your place that you arrive to should look like this after about 90 seconds. Show of hands, anybody here yet at a place that looks like this? Not yet? Oh, okay, well, one person. Anyone else? Oh, beautiful, yep. I'll wait for all of you to get here. And I'll walk you through this first one together very patiently. And then the next ones, they will progressively get more and more difficult. Let me zoom in here. Oh, and I have fun quizzes along the way. So pay attention to things that I say and things that you do. Show of hands, who is here now? Who is at this place? Oh, and I also have at least, I have 3 fantastic TAs. They're over here in the front. If you need any help, and I have Melanie in the back, if you need any help, raise your hand, they will come by and help you out. Before raising for help for hands, who is at this point now? Got 1. Please raise your hands high so that we can proceed. We only got 3 or 4 people? Okay. 5 people? Okay. All right. I'll proceed slowly while you guys boot. And if you need help, raise your hands. RTAs are sensational. So this is an instruct environment. Pretty much everything has been created here to make it easy for you to write some code and also interact. Each of these tabs that you will see, these blue buttons, they're clickable. You can click on the worker tab. It'll take you to this terminal. This will take you to the starter terminal. We have the temporal UI, which is where our workflows will show up. We have a network control panel that will allow us to simulate network failures, for example, turning off access to geolocation APIs, IP address, and so on. And we have our code editor, which is where all the code will show up. You guys will do work out of the exercise folder. The code will be relatively simple. It's Python code, but it'll be really simple. You'll basically just be uncommenting some code to make things work. But if for whatever reason you stumble, inside of the solution folder, there's an exact layout structure. You can just navigate to that folder, and it will show you the solution to the challenge. Let me see what else I need to show you all in here. Oh, and since this is our first exercise, we can walk through it all together. So here we can see writing the agent part. We'll click the editor tab, which will take us here, and then it tells us to go to exercise tools workflow.py. In here, we have our temporal workflow. You'll see we have a bunch of imports. We're importing OpenAI Agents SDK. We're importing some tools that we created. Ultimately, these tools are just web requests to different endpoints. This is a web request to get coordinates. This is a web request to get IP address, location info, and weather. All of these exist right here in tool activities. You can see here's our tool calls, which are ultimately just functions. You can see we've wrapped our tool calls in activities so that they become durable and reliable. We give our LLM a system prompt. Whether this is a great system prompt or not, we can debate later. And here begins our workflow. We provide a workflow definition. And here we start our workflow execution. And inside of our workflow, these are going to be the business operations that we want to perform, the steps that we want to execute in order to perform whatever we want to perform. We can have one workflow. We can have thousands of workflows. It doesn't matter. It's the steps that you'll want to perform. In this case, your goal, as you will see, there's a to-do statement here. It will tell you exactly what to do. Since this is our first one, I'm taking us through this. Little by little, I'll reduce the amount of hand-holding I provide. So in this case, it's really simple. We will uncomment this agent so that we can see how to construct it within our workflow. So I'm just going to go down here, uncomment. I recently got really good feedback on this workshop from one of our customers that not everyone is familiar with VS Code keyboard shortcuts. It's Command / to uncomment. And if you're a Windows, I don't know the command for uncommenting. I'm so sorry. And so we uncomment our agent. We can see the setup. This is using OpenAI Agents SDK. It's our integration with them. All it does is call out to the OpenAI APIs. We just put a beautiful wrapper around it just to make the code cleaner and easier for you to use. Provide a name, give it the system prompt, pick the model. GPT-4o is good enough for this one. Provide our tools, which are self-created API endpoint calls, right? Remember, these tools can be just web requests. It could be calls to MCP servers. Could be so many options. We provide these tools. We're providing them as activities tools, meaning that they will be wrapped inside of temporal durability. And so every one of them, if it ever fails, will get the durability behind the scenes or in front of you as well. And then ultimately, we'll run the agent and return the final output. So let's see if we performed everything that we needed. We did this step. That's pretty much it. For this one, very simple. Now, we want to execute our process. The very first thing we want to do is spin up a worker. So just click on the worker tab, click this run button. No need to even copy and paste in here. It'll start a worker. The worker is the process that will keep polling our task queue to decide what work it needs to perform on our behalf, right? We may have a backlog of things that need to be performed. The worker is the thing that polls the task queue to see what's in the backlog to execute. Once the worker has started, we can do our starter. The starter is exactly the code that you just saw, but we're just starting the workflow. And in this case, we're simply asking our LLM, what is the weather in Tokyo? And so we will execute this by going to the starter tab, hitting run. It will ask the LLM this question, and we will see how it responds. To see how it responds, we'll navigate to the temporal UI, we'll do a quick refresh, and our workflow already completed. Let's open it up and see what happens. So, of course, this is using our Python SDK. As I mentioned, we have many. This is one of the really cool things about temporal. I'm totally new to temporal. I didn't even know about it until I started working at this company. But one of the things that I really love is the visibility that we get to track every single interaction that's happening within our workflow. So, for example, you can see the entire timeline. Here we invoked the model activity. Here we got the coordinates. Here we invoked another model activity. Here we got the weather. And then we invoked the last model activity. We can click on these and see exactly what happened. We get a bunch of information. We can see the headers. We can see the input that was provided, right? And so you can kind of see what was the input that we sent to OpenAI in order to make this happen. Of course, everything that we showed in the code, but then also everything that was also abstracted away so you don't have to deal with the things that are not important. So here's the input, and we can see its output as well. If you scroll down here a bit, this is the result of that web request. And so this is what happened. It came back with a response ID and blah, blah, blah. Less important here. For example, but what happens when we called our get coordinates activity? So here's what it sent into the get coordinates, which was just Tokyo. And here's the output that it got back to us. Tokyo, longitude, and latitude, and so on. Get weather, same thing. Here's the input using the longitude and latitude that we got from Tokyo. And what's the output? It gave us the information. It gave us the weather. Let's see what the weather is there. Looks like temperature 79.6 degrees Fahrenheit. It even gives us the wind speed and so on. And ultimately, of course, we can see all of that inside of our CLI because that's what it came back with, 79.6 degrees Fahrenheit with a light wind speed. Let me see if there's anything else valuable to cover here. So good so far. Show of hands, who was able to successfully run their first workflow? Ooh, love it. Awesome. Congratulations. Great job, everyone. All right, we'll make it a little bit more fun. We will break it and actually simulate durability in real time. In this case, navigate to the network control panel. This simulates real failures. It'll turn off access to different kinds of APIs. In our case, let's go ahead and turn off the weather API, right? You can imagine either your network is blocking that call, maybe you work in an enterprise and they don't want you to talking to the weather API. Maybe the weather API is actually down. Maybe AWS is down, hence the weather API is down. So it's off now. Let's do the same exact thing. We will come back to our starter. We will run the same query, but in this case, it looks like we're asking what is the weather in London. And of course, you can switch it up. In fact, could have made it even more fun and said what is the weather in UC Berkeley, but we can do that next. We run it. Now, let's go back to the temporal UI and see what happens. This is the cool part because this is where the durability comes in. First of all, you'll see that now it's in running state, and it will stay in running state until the problem is resolved. You will see over here, this call, it keeps retrying. And it will keep retrying depending on the default retry policy that we've defined. In our case, we have a default retry policy. We didn't explicitly specify anything, and so it will keep retrying forever. There's also automatic backoffs and backoff coefficients that exist in here as well, right? Give you guys an example. You don't want your LLM, for example, to poll an OpenAI API all the time because, right, that'll cost you resources. And so maybe if you made 10 calls, you want to wait for 10 seconds before you make another 10 calls. And if those 10 calls fail, maybe you want to wait for 30 seconds before you make another 10 calls. And so that's called an exponential backoff. And so that's already built in here automatically. Normally, if temporal doesn't exist, we got to code this logic ourselves. We can get it can get a bit hairy, but because it's temporal, this is what's happening. And so you'll see the last failure, service error 503, service unavailable. And so that's what's happening. And it'll keep retrying based on the criteria that we define. We can define it explicitly, should we choose so, because we have some specific business requirements, or we can leave it in its default state, which is exactly what you'll see here. So let's fix the problem, right? Let's imagine AWS had an outage, it's back up. Weather API is back up. Turn the weather API back on, and within a few moments, we should see this recover as though no failure ever occurred. We don't need to touch any code. It'll pick up exactly from the place where the failure happened. No extra resources have been utilized. The workflow will finish correctly. We can go back to our terminal. And we got the weather from London, which is right there. Who has been able to successfully replicate that? Fantastic, you guys are so good. Let me see here if anything else I want to show you all before we move on. Maybe just one thing to point out to you all here, because this is using OpenAI Agents SDK. You can make your own. You can make your own agentic loop for sure. A lot of the agent frameworks, they hide the agentic loop behind the scenes, but ultimately it's a while true loop where you do the exact operations that I mentioned. You wait for user input, decide whether that user input, decide whether you have enough information to make a decision. If you don't have enough information to make a decision, what do you do? Do you call tools or do you do something else? You could do that all yourself, which will probably be about 50 lines of code. In this case, it's just one line of code. We're using activity as tool in order to provide the durability to all of the tools that we are calling. And then we're using the SDKs. Here you pretty much define everything on your own. So like this would be a self-made agentic loop that would exist. This is using the OpenAI Agents SDK. You just do run.run, and then OpenAI Agents SDK handles the loop for you behind the scenes. You just pass in the agent and the query. Here's the lines of orchestration code that you would need to write yourself should you decide how to work with the agentic loop. Here is, again, the SDK replaces all of that. The durability, should you want to execute the workflows, looks like that. Cool. That looks good to me. Everybody good on this point? Show of hands if that makes sense. Beautiful. All right. Let's we can hit skip and move on to the next. There'll be another module. It might take a few seconds to load, but let it load while I have a fun quiz for all of us. Please join our fun game. There will be quiz questions that we answer, and there's a little leaderboard that we can compete on. And maybe for the top 3 people, we will give away some swag. So afterwards, I'll grab your information, and the top 3 people will get some swag from us. Yeah, join. While people are joining. These questions are single choice or multiple choice. Some answers will have multiple responses. And the faster you answer, the more points you get. But of course, getting the right answer is also important. Oh, love it. You guys are awesome. So many people participating. This is my first ever public workshop for Temporal, so I'm super excited to see all of you guys participating in this. Thank you. All right, everybody joined? I'm not seeing any more people joining. All right, we are beginning. You snooze, you lose. I have cool music here that's playing. I guess you guys can't hear it. Hopefully most of you guys get this. This one should be an easier question. All right, congratulations to the 41 people. Yes, the LLM decides which action to perform next. Ultimately, the LLM is the decision maker. We pass it context, we tell it tools. The LLM decides whether it has enough information and what to do next, whether to call more tools or to give you back a final response. All the other stuff was just a distraction. Demo 2 is the one we just did. I hope like 99% of you guys get this right. All right, great job. Yes, in this case, we didn't write any loop. I showed you how a potential loop that you write can look. In this case, we're using OpenAI Agents SDK. The loop is written for us inside the runner.run. This one I might not have covered too well. I'm so sorry. Hopefully some of you caught it as I was going through the workflow, but I should have done a better job of covering it. But let's see. One of the answers is definitely not, right? The other two, it's like, yeah, maybe. Yeah, good job for those of you. Yeah, it could have been one of these two. It's invoke model activity. If we look at here in the next section, oh crap, because I don't have the workflows in here. I'll show you all next time when we get back in here. It's invoke model activity that is called. This is like our core reason for existing. Is this a hard question? LeBron is unhappy about this question. I'm sorry, LeBron. Yeah, great job to the 41 people. The reason why we wrap OpenAI LLM calls or any LLM calls in activities is because they're non-deterministic. And so any non-deterministic code We want to have an activities so that we can replay that afterwards. We want to keep the deterministic code, which is just the business logic, business flow inside of the workflow. Non-deterministic parts, put that in activities so that we can replay them when necessary. All right, we will come back to this after the next section. Oh man, I am so short on time. I think I got like 22 minutes. All right. Show of hands, I'm going to offer you guys two options of what we can cover. We can cover human in the loop, or we can cover multi-agentic processing. People for human in the loop? People for multi-agentic processing? All right, we'll do multi-agentic processing. So for that, skip this demo 4, human in the loop. The next one will be multi-agentic. We'll skip this one. I knew the hour would fly, but again, I'll share the repo afterwards, and you all can follow this workshop along and dig into it as much as you want. And then, of course, we're all here. We have a Slack community, temporal Slack community. You guys can reach out to us there for help. And then you can find me also on LinkedIn, and I'll be glad to help you all as well. Let's proceed. We'll skip human in the loop then. Sorry, all the human in the loop people. Orchestrating micro agents. So far, what we've done in our workshop, which has been really fast, we have an LLM, which becomes an agent, right? Because it runs in a loop. We've given it some tools. We didn't give it an MCP tool in this workshop, but we can. Had we done the previous chapter, we also would have added a human in the loop tool, which is ultimately allows us to ask and wait for human feedback, right? For human in the loop, you can wait for an approval, you can wait for some kind of information. That's ChatGPT. ChatGPT is a human in the loop type of thing, right? How does it wait for you to respond to it before proceeding with the next operation? But this is becoming very busy. And so we want to break this up. That's when we're going to create multi-agentic processing. A few reasons why we want to break that up. I'm going to fly through this because I want to make sure you guys get hands-on. Context poisoning, distraction, context clash, and confusion all can lead due to having too much context, right? Maybe for a smaller workflow, it's simple. For larger workflows, more data, the more stuff we provide, the harder it is for the LLMs to reason about. So we're going to break this up. We're going to have tools. We're going to have a weather agent and a Formula One agent that we're going to call, and we're going to have a personal assistant agent. Our personal assistant agent is going to be the entry into the entire process, our ChatGPT, and then using our query, our ChatGPT, aka personal assistant agent, will decide which tools it wants to call, whether the weather agent or the F1 agent, or maybe both, or maybe more. Few ways to call our sub-agents. We can call them via an activity. We can call them via a child workflow. You can imagine you have one business process that's running. Maybe you put a decision process in another, you put the decision-making logic in another process, which we call a child workflow. So you can have the main workflow starting a child workflow, or you can do that via Nexus, which is our other technology that ultimately allows you to segregate based on team domains. You can segregate based on regions. You can segregate based on security concerns. You can segregate based on code requirements. Maybe you want to have one agent being deployed at a different frequency than another agent. This is a massive topic, but if you guys want to know more information about it, just Google Nexus and then you'll learn more about it. But you'll see it being used here, but I won't cover it so much in depth. That's what that looks like. Cool. Let's actually build it. So at this point, you should be at this step, which we're calling demo 5. And all of the agents existing in their own workflow. So make sure you get to demo 5. Let's start it. And I will let you work your way through this. Oh, no. Let me quickly work you the architecture. There's an architecture diagram that I've added here from one agent doing one thing to 3 agents existing now. There's a lot going on. This architecture diagram is kind of meant to help you connect all of the pieces. I'll quickly walk you through it so that everyone can be hands-on. We start here at the personal assistant workflow, right? As I mentioned, personal assistant will capture all of the information. And we ask the personal assistant a query. What's the weather for the next F1 race? The personal assistant will then decide, what do I need for that to happen? We have F1 tool, which is a Nexus operation that will call our F1 agent, right? It'll execute in a separate file using a separate task queue, and it has an entire process that it will follow here in order to execute this. Here, we'll walk through it. I'm not, do all of these steps. Ultimately, the F1 agent, all it does is call to F1 MCP server, which we're hosting, but it's just calling ultimately to the F1 APIs. All that information makes its way back to our personal assistant agent. Now it says, okay, do I have enough information or not? In this case, no, because we also wanted to know the weather. So now it has to call the weather agent. So it's going to call the weather agent as a child workflow. Again, we're doing all of these different operations just to show you guys the different possibilities. Of course, we can code this in whatever way makes sense. This child workflow as a tool will be a separate workflow running on a different task queue using a different agent that will go through this process of deciding what is the weather in the location that we want. And so in this case, it'll call our get coordinates activity. You've seen that. It'll call our get weather activity, also tools. And ultimately, those are just public HTTP requests that gather the information and bring it back to our weather agent, which will bring it back to our personal assistant agent. With all of that information, the personal assistant agent can now give us a final response and say, at the Singapore Grand Prix, expect 30 degrees Celsius. That is what we are building here. Of course, more complicated than this, but I leave it to you all to now give this a shot, step through here. It should not be much more difficult than what we did, but follow along. You'll wire up the orchestrator by going in the editor and uncommenting some code, and then you should be able to run it on your own. I'll give you all like 1 minute, and then I will do this myself with you all so I can walk you guys through the important parts. I'll start slowly walking through here, and yeah, we'll go in the editor, go in the exercise folder. Inside it, we have a lot more files. You guys can see how quickly these things can get super complex, and so hopefully you guys are kind of understanding how complicated it can be to manage a distributed system. And this one is tiny. We'll navigate to our personal assistant.py file, which exists right here. Again, if anyone needs any help, we have sensational teaching assistants here that can help you. They are way more intelligent than I am. Very similar layout to what you guys have seen before. This is a personal assistant, gets a system prompt, gets some tools. Here's the workflow definition. Honestly, like getting started with temporal, for me, the biggest challenges were, number one, understanding the model of how it works, which is like, okay, if I want to orchestrate anything, put the process in a workflow, and then think about like, okay, what are all the non-deterministic things that I'm doing? Pull those out and put them in activities, which are just functions, right? Put those in functions, and then put those functions together in a sequence in the workflow. And so once you overcome that gap, the rest of the stuff becomes really cool and really easy, because all we do is code for the happy path. We just tell the system to do what we want it to do. The failures will happen along the way, and temporal will just be there like holding the queue for us, holding the history for us until we decide to proceed forward. So in this case, we're going to uncomment the weather tool block. That's what this is. Previously, remember, our weather tool was just a function and we called an API. In this case, we're going to call it as a child workflow. It means the personal assistant workflow will start a new workflow, and they'll be tied together. I'll show you how. Give it some information. In the second part, we're going to uncomment our F1 tool. Our F1 tool is ultimately an API call. We're going to call it through Nexus. Nexus, you can basically think of as an API that whatever team wants to expose, and the team, of course, can expose whatever they want. If I want to expose to you only certain endpoints that you can call to maybe another team or maybe another organization, you can call those endpoints only, and that's it. And that's what makes this really nice is you basically provide the endpoint, you provide the name of the service, and using that information, the workflow can call that endpoint, and whatever happens behind the scenes, we're going to call an F1 API. It could be many other things that happen behind the scenes. Those things can even change, but this contract will remain the same, ultimately allowing the caller to not have to change their code, but behind the scenes, if you want to improve it, we want to move to version 2, and so on, we can. And then we give it a tool description. Let me see if anything else. Here's our personal assistant agent. And make sure that the tools are included inside of our tools object. And then we continue running it as before, using runner.run, and so on. That looks good to me. Let me see if we accomplished everything. Fantastic. Now, because we have multiple workflows, we're going to use multiple workers as well. So let's spin up our personal assistant worker. You can imagine all of them as separately deployable units. Our personal assistant worker is running. We can start up our F1 worker, run that. Let's go to our starter. Let me see what, okay, we can do this call. And then we will ask, when is the next F1 race? And what's the weather there right now? And run that. And this is all real, of course, calling out to real APIs. Now it's running. Let's go to our temporal UI and see what's happening. Refresh. There we go. We got two workflows that are executing. We got our personal assistant. And remember, we started a separate workflow for asking for the weather. Let's go inside the personal assistant and see what it's doing in here. Inside of the personal assistant, we can see the input, right, which is the original query that we got. And we can see the output because it's already went through the entire process. Tells us that the next F1 race is in the Dutch Grand Prix, scheduled for August 23rd. And the weather is 64.7 degrees Fahrenheit. Here are all of the steps that it executed. Here's a call to Nexus. We don't need to dig so deep into that, but it basically allows us to call a totally separate, you can, as I mentioned, it's basically calling an API, and behind the scenes, the API performs its separate things. We can see it here, Nexus link. We can click on the Nexus link, navigate. Inside of that Nexus link is another workflow, the F1 expert, that performed its own operations. Here's everything that it did. It gathered the F1 data, called the F1 API, returned that data back. And then the personal assistant workflow, weather agent workflow, called the weather agent, gathered that data, and then returned it. And then using all that information, it was able to give us the answer back. Now, we can try to break it. I'll give you all a moment to break it, but ultimately, you can just turn something off. Let's turn off the weather again. in the network control panel. Turn off the weather and go back to our starter, rerun it. But we can, yeah, this is fine. We'll rerun this query again. We'll go back to our temporal UI. We'll have two workflows executing. Clearly, they're not going to finish. Let's see where it breaks. It's going to break at the weather agent workflow, right? You can see that now this is here. And it's continuing. And it's going to continue running until the issue is resolved. If we go back to our Ask Weather agent workflow, this is what's happening here. This call of get coordinates is the one failing. And it will keep failing until the issue is resolved. Let's fix it. Turn that back on. Go back to the temporal UI. Both of the workflows will start up as soon as they realize that the API endpoint is back up. Give them a moment. The restarting depends on the retry policy and exponential backoff, right? Sometimes we might get to a point where we have to wait for like many seconds before something is retried because we've been waiting for something to happen for a long time. There we go. Both of them completed successfully. Cool. Who here has been able to successfully make their agents fail? Beautiful. All right, well, let's wrap up with the quiz. Hold on, that means I have to skip a few questions. Get back on your mobile phones. Oh, here's the leaderboard for now. Let's see. YB is rocking it with Varghese at a close second and Ming at a close third. Let's see what can happen with the results after this quiz. You guys get in here. Is everyone in here? A bunch of people joining. I love the emojis. Keep going. A bunch of people joining. Join, join, join. Who's going to get the swag? Who wants the swag? How badly do you want this swag? I know, everybody wants swag. We'll do so much for swag and coffee, right? We'll do like anything for swag and coffee. All right, I think everyone's good. Oh, Varghese joined. We needed Varghese in there. He was number 2, I think. We still have people joining. All right, let's go. Let's see. You guys should be good with this one. Ah, no, Ask Weather Agent. That's not a specialist. We had child workflow as tool using as a temporal primitive. But it's also on me. I didn't do the best job covering it because I had to rush. I'm sorry. Let's see this next one. So this is if we didn't uncomment the tools inside of the tools object. What do you imagine would happen? We have the workflow, but the tools have not been added. This one is tricky. Tricky for beginners, for sure. Let's see. All right, yeah, it was a hard one. The activity will still run. We just don't have the tools to call. The workflow will still start, but we don't have the tools to call, so it'll just return with invalid information. I definitely talked about this. What is the value of getting the workflow execution, and wrapping those specialists in those workflows? You guys saw it in the UI, what we get. One of them is definitely not. Let's see. All right, yeah, great job, guys. That's really good. Yep, you get all three. You don't get more RAM, sorry. You got to pay for RAM on your own. 1 minute. All right, well, this will be the last question. I got 1 minute. Yeah, this one is hard because it's Nexus specific, but basically, instead of calling one workflow from another, remember what I told you Nexus is like. It's an API. So what does an API give you that that direct imports in your code don't give you? All right, yeah, you guys got some of these really good. Yeah, you don't get extra operations. APIs don't do anything for that. Namespace consistency, that's on the developer to define. Beautiful. Friends, that's it. I'm being kicked out. All I ask from you all are two things. Please follow me on LinkedIn. I will drop all the content that you saw here on there so you can get it. And then number two, in your Instruct, there's your feedback tab. Please just give us some feedback so that I can use this to improve the workshop for the future, and give me constructive feedback that I can act on. You can tell me I suck, no big deal, but please tell me why I suck. I would love that. And then also the winner, oh, let me let you all scan that. Everybody scan that. And let's check the 3 winners of the quiz. All right? And the 3 winners are Anton, Henrik, and Ming. I'll be in the back. Please see me after. I got you guys with swag, okay? I'll be like right in the back of the room. Thank you all so much. Have a beautiful day.
All right. Thank you for the great workshop. Now we're moving on to continued talking sessions. We have Doa, Principal Applied Scientist, Microsoft, with Mindful Agents, Human-Inspired Memories for Long Horizon Tasks.
That's okay, no worries. Hello, everyone. It's great to be here. I'm from the Microsoft Fabric AI team, and I'm here to talk about the work we're doing in the real-time intelligence space on our long-running agents, where we take some inspiration from ourselves as humans to improve the memory so we can get better at accomplishing tasks. So in the space that we're working at, we tend to have long-running agents that has access to data that's high volume, streaming data is high volume. And to just like set up the problem that we're dealing with and the motivation for the approach that we're implementing here, I kind of want to contrast it to how we as humans store memories and how like we tend to have the situation for our agents instead. So as humans, we have like storage constraints. So what's likely to happen is because of that constraint, we will tend to, the limit makes us better at distilling memories. So for instance, recently, I was on a train ride in Europe, and as you're on the train, you look outside the window, and you pass by endless fields, and you see some maybe windmills, you see some animals grazing, and we don't have the capacity to necessarily remember every strand of grass or every bit of thing over there. What we're good at is being able to distill that information and just remember interesting things that might be relevant to us. And this is just something that we, through evolution, are good at. Whereas if you think about the agents, we don't have that problem in terms of the storage constraints. We can log every bit of information, somewhat like relatively cheap, and we can log every trace. And what we do is we capture, retrieve, and typically we summarize and retain the summary. So over time, we are with summaries of summaries of summaries, which typically works well until at the time of retrieval when you're looking for something very specific for most cases. But for the case that we're working on, we're interested in getting agents that work with these like big volume data sets, and we want them to be proactive. So what we worked on is we are working on building a memory lifecycle as a feedback loop for our agents, where we have a system that starts with first ingestion, where we basically ingest all of the data from the observability substrate. And then what we do is consolidation, which is kind of like similar to the idea of sleeping. But what we do is we dedupe, merge, and we try to consolidate all of the memories that come in to become candidates. And the idea in here is, while this is similar to maybe humans, the consolidation cycles for the agents that we're working in are domain dependent, and they might not always be temporal. So I don't know how many of you are still in the room, but you were just building an agent that was like looking at F1, for example. So if you're a person, like if the agent is working on Formula One races, the telemetry that you take during the race will be very different from what happens after the race, like during the race days versus the off week, and then it's going to be very different from the season. So consolidation doesn't necessarily mean it has to be daily, but you need to process in some batch, in some cadence. Next, we have a forgetting, where there's decay and interference, and the idea is we want to make sure that if we have all these consolidated memories that are stable candidates, we want to make sure that we end up remembering the important things, and all the unimportant stuff gets forgotten, or most of it as best as we can. And then the next stage is retrieval. So for the retrieval, what we work on is a hybrid way where we have these memories stored in the cold storage, where we know a domain and put them in a graph, but we also have the live data coming in, and we want to make sure that the agent can access both the streaming data and what's in the storage that's more stable, and be able to determine what's the best memory to use at the time. So that gets us to the feedback cycle, where at the time of the retrieval, you will have usually conflicts. So something new might happen, and it might conflict the memory that you have established that became stable in the cold storage. That's where maturation and reconsolidation comes in, because we don't want to necessarily keep adding a new memory over and over into the graph that's very hard to retrieve from. So you need to determine whether you want to update an entity in the graph, whether you want to add a new entity to the graph because there's some new information that's important, or maybe discard what's the live information that's coming in because it's erroneous. So next, I kind of want to talk about all of these bits are there each their own components with different optimizations that you need to make. So I want to chat a bit about how we approach our evals for them and how our thinking around it. So here's two cases where we evaluate kind of like the ceiling and the floor about the best case scenario and a very tough scenario, where on the left side, we're having a retention benchmark, which is more deterministic, where in this case, we are looking at a case where the system has clear labels of everything that's important. So what we were looking to optimize in here is like how often we want to consolidate, and what's the kind of the cadence we want to use for it. And for this case that we were looking at, and this changes from domain to domain, but things started stabilizing around 500 events at a time. Sorry, I think 200 events at a time. It's kind of small to see from here for me, but let's see, yeah, 200 events at a time with a precision where if we like forgot over it, that got better. So like we're checking it, what's the best precision you get with how much you consolidate, how often you consolidate, and then how much forgetting adds over it. In the next case, we were using a retrieval benchmark utilizing long mem eval, where we were looking at how much compression should we have, what's the optimal storage size we should look for without being destructive. So this is an eval where it's conversations, so we have no labels about what might be important or not, which is not the ideal case for the type of work we're doing, because the idea that we have is these domain experts that do repeated tasks, and there's an idea of how you can learn what's important. But even then, we can like optimize, and there's a trade-off between how much you want to compress and what accuracy you get. So with that, the kind of like approach in more general is for the type of memory work that we're doing, we need 3 types of evaluations, and they kind of have like different ideas about what they're looking for. So one of them is retention, which can be a quick eval on deterministically, if you're building a memory system, and if you want to keep the important information, can you just can you make sure that what you're keeping is actually important versus not? Which is, you need the labels for it, and there's a lot of work that we're doing on like how we get better labels. But then the next one is retrieval. So assuming that you built a good memory system, then you need to look at how well you're retrieving from it, and are you getting the memories that you're looking for in that like great system you built? Because if it's hard to navigate your memory and it's hard to do the retrieval part of things, then that still like is necessary but not sufficient. So you want to have good retrieval. And finally, you really, for the agents, you want to look at your task completion evals, which are the most important because it's closer to the user. You might give the best memory to the agent, and depending on how it's exposed to the agent in your harness, the agent might choose to ignore it and still might not accomplish the task. And this is kind of like the most expensive one because for the long-running agents, it is kind of expensive to build and run the evals, but it's the most important. So like for each component, we're focusing on these 3 things. So to kind of just sum things up, logs are not memories. And I think like where things are going is like for long-running agents, you want to make sure that you have more than just the traces that's going to become available to them as memories. And the way like the volume works to be efficient, you'll have to figure out how you keep the important things or not. And then another important point is the domain is important, and like for these cases, it needs to be pre-declared. And depending on how well you can do it, at the runtime, you need to have it prior, otherwise that affects the efficiency and accuracy of the agents that you're running. So in terms of the next steps we're working on, we're working with the Microsoft Foundry team on end-to-end evals in StateBench, and we're also doing some work on better work on domain learning and graph ontology, where the idea is what we found in a lot of these is the way you set up your graph structure and the ontology for it has a big effect on your accuracy in addition to these components, so we're working on them. So with that, thank you very much, and I look forward to meeting everyone after. Thank you.
Now we have Ian Fisher, CEO of Poetic, and optimization perspective on recursive self-improvement.
Okay, yeah, my name is Ian Fisher. I'm a co-founder, co-CEO of Poetic. And Poetic, if you haven't heard of us, is a startup we founded about 1.5 years ago that's entirely focused on recursive self-improvement. So we're building AI that improves itself. And in the past year, and a little less than a year, our focus has taken us from nothing to a system that automatically can set state-of-the-art on a wide variety of major public benchmarks. We're 10 scientists and engineers, mostly from Google DeepMind and Apple, Microsoft, Amazon, ByteDance. Some of our early results we had on reasoning and knowledge extraction, setting state-of-the-arts on all these, and coding. So let me dive into this. I want to define carefully what RSI is. And so, it should be really simple. There's only 3 letters, and really 2 of them are doing all the work here. So recursive means that the new improvements at each step are going to drive the next round of improvements. And self is the system really is going to improve itself, not some other target. Improvement is really obvious. Everything, everybody's doing improvement of some sort. But RNS really come together as a pair. If you don't have both of them, you really aren't doing the right thing. And the reason that I'm being a little bit pedantic here is that common use of RSI is both too permissive and too restrictive. So some people have described approaches as being RSI that are really just a standard iterative improvement loop. And other commentators, other people think that RSI is something that's only RSI if you are improving the parameters of a large language model. And this is too restrictive because there are a lot of other pieces of an intelligent system that can be improved quite effectively. And so why does RSI matter? We think that this is, RSI is the most important frontier in AI research because the improvements of real RSI systems compound. And this is going to lead to superintelligence much more quickly than human-driven improvements are likely to achieve. For the obvious reasons that humans don't become inexorably smarter while improving models, but RSI systems can. So I'll talk a bit about the landscape here. We can split RSI approaches on 2 axes. On the y-axis, going from cheap at the top to expensive at the bottom, and on the x-axis, going from things that really aren't RSI, so just standard iterative optimization approaches on the left to things that are RSI on the right. And so, the upper right quadrant here is a nice place to be. Of course, we put Poetic there, but that's not arbitrary. We put ourselves there because our loop does in fact compound. It really is RSI, and each step of RSI only costs an inference run rather than a training run for an LLM. In the lower right are where the best funded efforts are. This is what people generally think of when they're talking about RSI. Again, the kind of this LLM-centric perspective where Anthropic, OpenAI, and Google are putting a lot of effort. And these are genuinely RSI, but they do require to train an LLM from scratch at every step. In the upper right, we have a few neighbors, and they're also genuine RSI, and they're also cheap, but they're a bit narrower than our approach. Like Darwin-Gödel machines and Sika are both targeting coding primarily, and the Minimax harness trains on some of its own generated data. So as I mentioned, you basically you can partition this landscape into 2 pieces, and on the bottom we have LLM-centric approaches that focus primarily on improving a particular LLM, and then on the top we have more systems-oriented approaches that view the LLM just as a component of a broader system that should be improved. And shifting from an LLM-centric approach to view to a systems-oriented view opens up a lot of possibilities for improvement that you would otherwise miss. Also, they tend to be faster and cheaper. So I'll talk a little bit about 2 of the really prominent approaches. One is what the recent Anthropic post, AI that builds itself, describes, where you take a version of Claude, you put it inside of Claude code, and then humans plus Claude code improve Claude. And so this is partial RSI. Clearly there's Claude is part of the system is the thing that's being improved, and it's part of the system that's improving it. But there are humans in there, so I kind of don't want to count them, and Anthropic doesn't count them either. On the right, we have another common approach called an automated AI scientist. This is similar also to auto research. And this is typically not going to be RSI. There's a number of nodes here that are doing different things. But basically, you generate, the system generates a hypothesis, and then it implements that hypothesis, and then it measures it, and then it like writes a paper about it and puts that paper back into some knowledge store. And this is usually is not targeting a piece of its system itself, so it's not actually going to be RSI. But we can make both of these into pure RSI systems. In the case of Anthropic, we can just get rid of the humans. They've kind of indicated that that's where they're headed, and that's maybe something that they're worried about. For the AI scientist, it's also a simple fix. You just target the LLM that you use in your in your AI scientist loop. Of course, doing that makes it much more expensive than what most people are doing with automated AI scientists. So what does Poetic do? So what we're doing is what we call self-optimizing optimizers. So what's this look like? We start with a general purpose optimizer, where a general purpose optimizer is one that doesn't rely on any specialized signals like gradients. It just requires measurable feedback from the optimization target. So this is more general even than like black box optimizers like hill climbing, because it doesn't have to be quantitative in nature. So then given that optimizer, that general purpose optimizer, let's use it to optimize something. So we'll have some optimization target. It's providing feedback to the optimizer. And as I said, the feedback here can be quite arbitrary. So there could be standard approaches like accuracy, cost, things like this, or more unusual feedback like rubric evaluations or reasoning targets. So once we have these two pieces, this clearly is still not RSI. This is just standard iterative optimization. But we have this, framework of a general purpose optimizer that we can then apply to the optimizer itself. So now the optimizer is optimizing the optimizer that's optimizing the optimization target. And this is now RSI. So in order to have an optimizer that can optimize itself, you only need two things. It needs to be a general purpose optimizer, and the optimizer needs to provide feedback about its performance. So since we started with a general purpose optimizer and every optimizer can do that, we don't have a problem here. But this is, I want to be clear, this is very different from saying that the optimizer is Atom or SGD, right? That would not work. So this is what we call the Poetic metasystem. It is RSI, and we use it to optimize everything. So every task that the metasystem optimizes helps it optimize itself, which makes it become a more powerful optimizer. And again, since it is a general purpose optimizer, we can point it at any part of the metasystem itself, as well as at any other measurable task, like benchmarks, the benchmarks that I showed you at the beginning, and customer data, things like this. So talking about what we, empirical results here, our most recent empirical results, we have this blog post that, where we pointed out that benchmarks are dead for us. And what this is really referring to is not that benchmarks aren't useful, but that in the presence of a properly recursively self-improving system, static benchmarks have fairly limited value because it is, we are able to fully automatically get SOTA results, state-of-the-art results on every benchmark we've turned it on. And so again, as I said, it's fully automatically, so 0 human interventions and usually quite quickly. So concretely, here's a table, bunch of results. The interesting thing, or one of the interesting things here is that on half of these benchmarks, which are across a wide variety of different domains that we've never worked on before, we got SOTA using older, cheaper models than whoever held the previous SOTA, typically Fable 5. What's next now that we're not focusing on benchmarks? We are working with early customers in a variety of domains. And I want to leave you with just this perspective on the frontier that the next phase transition in AI is going to come from a system that invents its own improvements. And so at Poetic, we're intentionally casting a very wide net for that phase transition, again, by taking this optimization perspective on RSI and using it to optimize everything, including the optimizers themselves. Thank you, and we're hiring.
And now we have Yusu, CEO of Neocognition, speaking on intelligence, continual learning equals expertise.
Check.
Right, perfect. All right, so today's talk will be quite conceptual. I will talk about three concepts: intelligence, expertise, and how continual learning bridges the two. But I think this is perhaps one of the most important conceptual questions we need to think about today, and it can help explain many of the bizarre observations we're having at the AI frontier. The first observation is that AI has gotten so intelligent. Like this morning, OpenAI just came out with solving 10 other major math problems. But on the other hand, their diffusion in the enterprise world seems much slower than everyone expected. And we are seeing an explosion of these forward deployed engineers and deployment companies to help diffuse AI. But if these AI are so smart, why we need FDEs to deploy them? Shouldn't they deploy themselves, right? Humans don't need an FDE to teach us how to do a job. So what's missing here? And then also, why, if we look at the value accruements in the AI stack, 90% of the value is going to the infra and the model layer. And the application layer is getting less than 10% and also often running at a negative margin. So why is that? And obviously, this is not a stable equilibrium for the ecosystem. So how can we solve that? So I think hopefully this talk will help explain many of these bizarre observations today. All right, so obviously, agents, particularly we call the current generation of agents language agents, because language use for reasoning and communication is their defining traits. And they already found their first mass market, which is obviously in coding. And the best way to see that is through the revenue ramp of Anthropics, right? Everyone has seen this magical story. But coding is the first mass market, largely because it's already a language privileged world, right? Everything is already represented symbolically and very well recorded and maintained. So that makes it perfect for language agents. But what if we leave the privileged world of code? Well, not so well yet. I think then the Netherlands project reported that we are having a lot of issues with deployment of AI in enterprise. Of course, this was from last year, and of course, you can argue about the 95%, the number, but I think it's directionally correct about the difficulties. And then we saw all of the bizarre failure modes of agents, and to the degree that Andrew Kaparthi last year went on the Darkash podcast to argue that 2025 was not going to be the year of agent, but it's going to be the start of the decade of agents. And he particularly mentioned challenges around computer use, around continual learning. Right, so I think what we're observing here is a really modern version of the Moravec's paradox. So remember the original version of the Moravec's paradox from the 1980s essentially says that for AI, it seems that hard things are easy and easy things are hard. Right, so they're particularly good at the symbolic reasoning tasks like math and coding, but very challenging to learn things that seems effortless for humans. Like back in the 80s, it's mobility and perception, but now we are seeing the difficulties in everyday digital work. And why is that? Here's my hypothesis. If you look at the modern society, it's really not just one unified world. It consists of millions of micro worlds. Every profession is different, every company is different, every company is special, that's why they exist. So every environment has its unique local physics, the structures, the constraints, the affordances, the dynamics. It's just too heterogeneous and dynamic for any static model that tries to compress that into one static representation. So you have to continually learn on the job to form specialized expertise. And then that leads us to the next chapter, that intelligence is different from expertise. For intelligence, we will focus on the LLM context, the type of intelligence that LLMs exhibit. Then it's really the capacity to solve problems. Give me the problem statements, give me the context, I will reason through this gigantic solution space and find, maybe possibly spin up like hundreds of sub-agents and try to find a solution for you. But expertise is different. Expertise is really accumulated and situated competence, right? It's the ability to act reliably and efficiently and with judgment to deliver superior performance on a particular job in a particular environment. Right? So hopefully through this, the contrast is very clear. And then what really does expertise contain? If we look into the literature from cognitive science, that can give us some insights. Essentially, when we are learning on a job to form expertise, it's the process of continually forming new mental representations about that job, about that domain, that allow us that will manifest in multiple different ways. It will allow us to see things differently. For example, if you're looking at a very long bug report from a crash system, obviously an expert versus an intern will see things very differently. Right? The expert will very quickly locate the plausible places of failure. And then expert can see the deep structure, not just like the surface patterns. The experts know that everything is conditional, that for every rule, there are a whole bunch of preconditions that you need to learn, like when that rule holds. But you also need to learn what are the exceptions where you can bend the rule against the reality. And finally, our judgment and taste, which we'll talk about a lot lately, also come from expertise. So from this, you can more or less think of like expertise is really a word model, right? It's a model of that micro world that manifests in many different ways, that becomes the foundation for our perception, for our reasoning, and for our decision making. Then we can further compare the two, but in the interest of time, I think what the most interesting here is to compare, like, intelligence is, at least the form of intelligence LLMs have, or expansive in nature, right? It tries to or just look for the context on the fly, tries to expand its search, and that as a result, it's, because it cannot accumulate from the past, as a result, it consumes a ton of tokens. Like at neocognition, we're burning like millions of dollars in tokens. But for expertise, it's contractive in nature, right? It's about the process of forming shortcuts, forming effective structures of the domain that will reduce your search process, search space. Okay, so next I will talk about continual learning, but since I only have a few minutes, so I have to be much faster. But continual learning is a very confusing term. So let me first try to give a unifying definition. I think continual learning is the process of adaptive compression of experience into reusable structures for future behavior. So all of these four elements are very important. And you need to answer, when you talk about continual learning or see some work in continual learning, you need to understand each of these four elements, what exactly is being talked about. So what kind of experience we're talking about, how you're compressing them, and into what kind of structure, and how you use that structure for future behavior, right? But the adaptivity here is very important. That the things that you compress in the past should determine like how you compress in the future. Then here's I think the most important and interesting part of this talk. This is the relationship between intelligence, expertise, and continual learning. If you put intelligence as the x-axis and expertise as the y-axis, you will see that they are largely orthogonal, right? You can get like more intelligent models, but if you don't have continual learning, then it will become what I call the world's smartest novice. Just tries to brute force its way through every problem using raw intelligence. That's why everyone's token bill is exploding. And different continual learning algorithms will essentially set the slope of your learning. So if the goal here is to have a very strong continual learning algorithm that give us very strong expert agents. And if we follow this setting, then the most interesting feature that we can derive from this is what I call unbounded expertise from bounded intelligence. What if there is a threshold for intelligence, we can call it escape intelligence, that once we cross that threshold, plus a strong continual learning algorithm, then we can get almost unlimited expertise, or at least good enough for maybe 90% or 95% of the jobs in the world. Then if that becomes true, that means a very strong bifurcation of the market. Right. So the frontier models, they will continue to build like more intelligent models, and there will be many use cases for those. But maybe for the 90 or 90%, 95% of the other jobs, we don't need more intelligent models. Maybe even current models are good enough. What's left is continual learning. So that will be a very interesting dynamics in the market. Okay, I'll skip this one. These are some open questions we can answer, but just a few seconds to take a photo. And finally, I think the expertise will be the next dimension for scaling. But for scaling expertise, the goal here is not to replace human labor. I don't believe in the job displacement narrative. I think we are in a great shortage of expertise. In an ideal world, everyone wants to have personal healthcare, personal finance advisor, personal tutoring, and so on and so forth, right? And every company wants to build its own learning loop, local human AI learning loop, that where the knowledge and the IP accrue. And finally, if we can scale, make expertise abundant, then it will lower the friction for many of the problems that will make a lot of new problems across the threshold of worth doing. So that will create a lot of new opportunities in the society. So I'll stop here, and thanks for the attention.
All right, we have lots to think about and a lot of information in a short amount of time. Next, we have Furong Hong for reasoning as control, adaptive test time, compute, and planning agents.
Actually, I think my talk is going to be towards self-improving agentic systems. And when people talk about self-improvement, oftentimes we frame it as a model capability. The model can actually improve its reasoning and then started to actually learn from its own output and hopefully acquire some new skills. But I think model is just one layer. At the end of the day, it's going to be an agentic system that is going to be deployed, and there are a lot of the infrastructure around the model, how the model is actually built. I think that's also a very interesting layer for us to understand how we can keep improving these infrastructure. And that could be even more important for very kind of vertical applications that, utilizing language models in your very own environment, in your corporate, in your own application areas. So now let's talk about what really happens in an agentic system. Given a task, standard slides technical difficulty. So given a task, right? So you will be observing, some kind of, state, transitioning from an environment, and then this kind of observation goes through your thinking process. And at the end of the day, you wanted to make a decision, right? Maybe at every time you're going to make a decision, what is the best thing to do right now? And in order for agentic system work, oftentimes because these tasks are very, very complicated, you wanted to decompose them into different agents, right? And you wanted to assign roles for them, and then probably you wanted to design some kind of workflow, like nowadays I think we call it loop engineering, right? So and then for each of the agents in your workflow, and you wanted to decide what is the action at every time step. And in order to do that, you need to go through a thinking process. Oftentimes, a chain of thought, right? For each action decision, the agent has to generate a reasoning trace. As you can see, there is this kind of hierarchy of decision-making during runtime, right? So starting from the very low level of thinking traces and token control, all the way to action control at every time step of your decision-making process. And then finally, in the very high level, workflow control, right? Can you optimize them? And I think today I'm going to say foundation models are actually more and more becoming a runtime decision maker. At the end of the day, the self-improving agentic system is possible that you can improve the model capability, but you could also improve the infrastructure, improve how the model is deployed during runtime, across thinking, across actions, and also across workflows. So let's talk about a little bit about what we did, think in each of these levels. Down there in the thinking process, I think we started with the steering problem, where you have some kind of reward model, and you're hoping that you can steer your large language model to align to the specific reward. Of course, if you're familiar with the math, you will know that you have a closed form solution. And it turns out this closed form solution gives you a very short answer to the very complicated question of alignment, which is, whatever your base model gives you, you just add an additional steering signal to it. And this steering signal is nothing but something related to a trajectory reward under some specific optimal policy. I know this is very complicated math, but at the end of the day, if you look at what it's really doing, if you're thinking about next token sampling from a language, autoregressive perspective, you're just looking at the language model's output, and then you just steer it with some kind of external signal that you can learn from your corporate data, right? So now, the actual discrepancy here, and sorry, I promise the slides looked way better on my laptop, but, in this situation, there is this discrepancy about you really want to next token generation. You wanted to steer your process as early as possible, but you can not because your reward model does not really support that. You have a trajectory level reward model, but what you really want is an early steering before you actually determine your thinking process. So what we ended up doing, for example, in the work, transfer Q star, we started to think, okay, if the reward models are really not designed for scale up, the every token sampling, let's just do the auto completion and use the reward model in the right way. Of course, this is right, but it's really, really slow. On the academic setting with my A6000 GPU, you can see if you have to generate 500 tokens, it will take you 14 hours, which is basically impossible, right? So you're doing it right, but you're doing it way too slow. So in a very recent work, we tried to improve it by actually come up with like a specific model family of reward, and we essentially designed a token level reward and significantly reduced the cost by orders of magnitude. And as a result, you can see this is phenomenal because you can do any runtime steering of the model. You do not have to train the model at all. You can even do weak to strong guidance. You can use a very small model to guide a very huge model. And then you could even do multi-objective alignment in the sense that if you have very different objective, you can real-time adapt the objective to the specific user need. So this is very cool. But what about the action, right? So we talked about steering your thinking process. But at the end of the day, your thinking process is really for service of your action. So how do you make the decision? Well, it is an agentic system, right? So we often know that agentic systems are learned using this called imitation learning, which is essentially distilled from expert demonstration. But this, oftentimes run into this kind of stuck loop problem where your agents will repeatedly try some actions for many times until termination or you run out of your token budget, right? So that's very sad. So people started to think, can we do some kind of, better, smarter ways of learning through some world model training, and specifically, people thought of like imitating self-reflection. But this is not actually self-reflection. When you are trying to self-reflect, you're not actually using yourself to reflect. You are actually mimicking some stronger model which teaches you how to reflect. And it turns out it works better than imitation learning, but it's not really giving you very satisfying result. So we did a very simple thing here. We call it genuine self-reflection. Rather than actually imitating how stronger models think and self-reflect, we force ourselves to do the reflection in terms of choosing which action is better at this time point. And you can imagine this is actually a world model. You're trying to build a mental model about which action is better under what state, but you're also forcing yourself to understand why. And this very simple thing, worked really phenomenally. You can improve imitation learning as well as reinforcement learning. It actually improves significantly out of distribution, distribution kind of performance, and also, performs way better than previous state of the art. So like this genuine self-reflection really, really helps. And also, I think one really cool thing is that it actually generalizes to a general reasoning by just understanding how agents work better in a specific environment. You can see this, kind of critical learning that's not related to any general reasoning capability, but somehow it magically improves the general reasoning capability. So now, control decoding can steer how the agent think, and then ACT can actually help your agent understand how to, under what state, what is the better action. Now, finally, I think what's really exciting is this kind of like workflow control. Autonomously decide what are your agent roles and how do you actually optimize the topology of the agents, sort of like the workflow optimization. So I have a very simple example here, but for the sake of time, just basically saying this is a very fixed workflow for like, agentic safety kind of application. It works, really well, but the question here is, can you actually design, such a framework such that you have a meta designer, as the query comes, you could come up with the best agentic framework, the best harnessing that is specifically for this very specific task. Well, can you do that, in an autonomous way, right? So people tried to do this. For example, they tried this thing called one for all, and they also tried this thing for one for each. One for all basically means that you're going to find the best workflow in the world for the specific task. And then one for each is that you have to find the adaptability, so that you can design the best flow for each of the query that comes into, your model. So it turns out we're thinking about this, kind of philosophy of foundation model, right? So we don't want to actually do one of these two, but we wanted to say, can we actually pre-compute the workflow and sort of like, during the training time, but then reuse them during the deployment time? And can we achieve efficiency through that kind of process? And it turns out what we did is we built a bank. We built a bank of workflows, and then during test time, yes, we're gonna just like adapt to the specific workflow real time, really efficiently. And as you can see, the result also worked really well. Like you can see significant improvement of the performance. I can share a better version of the slide that is actually rendering correct. But if you trust me, so you will see like the performance is really nice. So just to sum up, we talked about self-improving agentic systems. We talked about how there are 3 levels of runtime decision makings that you can be very smart about how to allocate your compute resource with the limited budget, how to steer your thinking process as early as possible so you do not have to go through the very lengthy kind of process of thinking but in the wrong way, how do you control action, and finally, how do you do the workflow control? And with that, thank you.
Okay, for our last individual speaker of the day, Raja Giris, professor at Tel Aviv University, on the visual compatibilities of multimodal models.
Hello, everyone. I want to thank the organizers and all the previous speakers for the interesting talks. My talk is taking a slightly different angle than what was presented before. So everyone here was talking about coding agents and how we can extend them. Here I want to talk about adding new capabilities and which is going to multimodal. So most current models focus on how to improve coding because it's easier to work like that. But when you hear me now, you don't just see a text. You see me. You see everything. So we live in a multimodal world. And the question is, what are the current visual capabilities that we have in multimodal models? So there are various challenges when we look at multimodal models. And I think that one of the interesting things that we see in the field is that once people start asking the right question, in 1 or 2 years, we start seeing solutions. So a few years ago, with my group, we had some works on compositional reasoning. There were some observations that one of the problems of old multimodal models, when they look at captioning of images, so for example, if I want to generate or want to describe an image with 3 zebras and 2 giraffes, so basically all the numbers and names are mixed together, and the model is treating everything as a bag of words. And then there is some problem with compositionality. And then with my group, we had various work on improving the compositionality, and since then, things improved. So we used some tree structures. We took the words and decomposed them into trees. We basically had more dense and aligned captions. And basically, we taught this model to be structured. So you can see them in these works. Afterwards, we found other problems that exist in these models. So in 2 works, we try to analyze what happens if you try to work with these models and see what happened in the workflow of understanding. So in one work that was done with my colleagues, which is called Performance Gap in Entity Knowledge and was published in ACL 1 year ago, we basically try to see where in multimodal models we can see the reasoning. And one of the problems that we see in current multimodal models is that basically if you look at all modern multimodal models, you have very strong LLM and a nice visual head attached to it. So we invest lots of resources in training LLMs, but then we have some nice visual language model that we found somewhere attached to it. We train them together afterwards with some post-training, and then when you analyze what happens when these models try to do some multimodal understanding, you see that most of the analysis that happen in the LLM part and not in the visual part. Another work, we try to analyze what happens if we try to do in-context learning. So in LLMs, we know that in-context learning is great, but then the strange thing that we found in VLMs or multimodal models is that if you give in-context learning that is too long with too many images, basically the models start to get confused. And again, the reason for that is that currently when we train multimodal models, we mainly rely on the language part, and the question is, maybe we need to make a certain shift. So the focus in my talk would be on a specific ability of multimodal models, which is spatial cognition. And there is an interesting work of my colleagues that was published 2 years ago, which is whether spatial cognition emerged in frontier models. And what they did is they checked various spatial cognition tests on multimodal models. And they checked some task like mental rotation. We get a shape, and then we ask which shape is basically the same shape but rotated. Another interesting task is perspective taking. I am asking where the dog, what is, for example, the angle between the bat and the dog? And then the question is whether such model can answer that. Another question is maze completion. We want to ask a model to solve this maze. And then another interesting task is shortcut discovery. In shortcut discovery, basically, you show a model a walkthrough through a place, but you don't go in the shortest path. And then you ask the model to go in the shortest path, and you check whether the model is capable to do that. So all of these are very important tasks in spatial cognition. The interesting thing is that 2 years ago, all the models were very bad. If you take the frontier models, like GPT and other frontier models, they would act really bad. But the interesting thing is that once you start asking the question, you start to see improvement throughout time. So this work that was 2 years ago, you get that frontier models are quite close to chance, they're a bit better. January this year, there was an interesting work called Baby Vision. They made a similar exploration, and then they found that on January this year, the frontier models were basically at the level of 3-year-old child. So from models that don't know anything, we grew up to 3 years. So the interesting thing is that you see that once question is asked, sometimes it's more important to ask the question, people start to pursue that, and in 1.5 years, we got to 3 years, which is nice to grow to become 3 years old in 1.5 years. But usually we want to grow slower. Another interesting work, which is compared how much time it takes for a human to solve a problem, and then compared this time to what the models can do. And basically they found that current frontier models, and this happened in February 2026, can solve spatial cognition tasks that take for us as human 10 seconds. So if you think about it, like mental rotation, maze solving, it takes us some time to solve. So these models are able to solve only the tasks that we are able to solve in 10 seconds, which is not so great, but better than what we had before. And then if we look at the tasks that I talked before, so here we can see the state of advance since the initial work I mentioned by my colleagues was published 2 years ago till today. So 2 years ago, for example, in perspective taking, the best models were close to chance. 2 years after now, we can see that, for example, Opus 4.6 and Gemini 3.1 are basically almost close to 100%. Very impressive improvement in just 2 years. In maze completion, we are still not so great, but just 3 months ago, from close to chance, we see that, for example, GPT 5.4 got a great leap. And the same happened with shortcut discovery. So we see that great improvement in these models. And then the question is why this happens. So in a recent work that I have done with my colleagues at Apple, we asked the question of whether multimodal models imagine electric sheep, and the answer is yes. So I don't have much time. I will just mention briefly, and then you can look at the paper. Basically, what we did, we studied various spatial cognition tasks, and we studied them in an open loop case. Open loop case means that we just show a model the first frame, and then we ask the model to try to solve the game by giving us what step it should do. And the interesting thing is that we found that if we look at the model that is not generating any image, it can receive images but cannot generate image, and basically we probe the weights, we can take a transformer attached to the weights, probe it. The interesting thing that we found is that the model is imagining internally how to solve the problem. So in different tasks, for example, if we ask if two shapes have the same chirality, we basically able to see that the model in its internal weights is reconstructing the visual thing that we would do. If we look at two shapes and want to understand if we rotate them, they become the same. So we found that the model is doing it in its internal weights. And maybe this is the reason for the great improvement that we see, that models started to imagine. And the same happened, for example, if we want to assemble characters. So we can see that models in their internal weights assemble characters. And if we see that a model that is not able to generate visual thing is able in internal way to do that, so what we done, we added the ability to the model to imagine, we supervise it to imagine, and suddenly we have seen improvement in performance by adding this imagination ability. So we have some more results. Because of time, I will skip them. But the interesting point is, or there are 2 points I want to mention. One is asking the right question is very important to advance science. Second thing is that if we think about multimodal models, it's very important for the models not just to focus on text, but also to focus on generating the visual part, and it helped the model to improve a lot. Thank you very much.
And now we have a workshop. This is on Open Agentic Stack, building the future of AI systems with open source, open standards, and composability, by the Linux Foundation. We have Matt White, former global CTO of AI Linux. We have Ben Burtonshaw, community engineer for Hugging Face. Daniel Han-Jen, co-founder of Unsloth. Sheng Yang from RadixArc. And Romeo Bardwaj, co-founder for SkyPilot. Come on up.
Just flip the switch? Okay. Should we be waiting for prescribed time before we start, or go ahead? Okay, because we're running like, I think we're 25 minutes behind so far. Oh, I'm not going to project. I'm just going to say something. All right, good afternoon, folks. We'll get started here, and I imagine some folks will kind of trail in. So thanks for having us today here. We are, I'm the former global CTO of AI at the Linux Foundation. I previously led the PyTorch Foundation as the executive director and CTO, and I'm a visiting scholar at Columbia University. So before we begin, I would like to share some thoughts as we are living through unprecedented times. AI capabilities are advancing at a pace that would have sounded implausible only a few years ago. Models can reason across long contexts, write and execute code, use tools, and operate software, and coordinate increasingly complex workflows. We are entering a world where powerful models can solve complex mathematical proofs, generate extensive code bases, and power systems that take actions in production networks that have real-world impact. But exactly at this moment, when AI is becoming more capable and more consequential, openness is under genuine pressure. So the idea of restricting or even banning access to open weight models is no longer a hypothetical, right? It's being actively debated in Washington and elsewhere, and we're also hearing proposals that to attempt to control the frontier through chips, compute, distillation, safety testing, and model release processes. The safety and security and national security concerns behind these discussions are real and legitimate. They deserve serious, technically informed responses. But we must also be equally clear about the risks on the other side. Blunt restrictions can concentrate capability, infrastructure, and decision-making to a very small number of institutions. They can transform artificial intelligence from broadly accessible and general-purpose technology into something that the rest of society is only permitted to rent from a few labs. That cannot be the foundation on which we build the future. Openness is how we create competition. It is how researchers inspect systems, developers adapt them, students learn, enterprises maintain sovereignty over their data and stack, and countries build AI capabilities without being permanently dependent on a single vendor. So openness is also an essential part of safety. It enables reproducible evaluation, transparent interfaces, independent scrutiny, shared security tooling, and the ability to identify and correct problems. Sorry. Oh, there's no slides. It's just me rambling. But open communities allow more people to test assumptions, discover vulnerabilities, compare approaches, and contribute to solutions. But openness does not mean ungoverned. It does not mean being careless, unsafe, or a free-for-all. Openness means that systems can be inspected, evaluated, adapted, and improved. It means that interfaces are interoperable, implementations are contestable, and no single organization controls every layer or decides who's permitted to participate. This becomes even more important as we move into agentic AI, because an agent is not simply a model. An agent is a stack. It includes the model, the harness, the tools it can invoke, the environment in which it acts, guardrails, the reinforcement learning systems through which it improves, the evaluation infrastructure that measures it, and the compute on which the entire systems rely. An agent may depend on APIs, credentials, sandboxes, memory, inference systems, orchestration frameworks, and multiple forms of specialized hardware. It may cross organizational, cloud, and geographic boundaries while completing a single task. If any one of these layers becomes closed and vertically controlled, the entire ecosystem becomes less portable, less competitive, and more fragile. That is why open models alone are not enough. We also need open environments so that agentic tasks can be reproduced and shared. We need open reinforcement learning frameworks so that more people can improve models and agents. We need open compute layers so workloads are not captive to one cloud or compute vendor. And we need open standards so all of these components can work together without requiring permission from a central platform. The open agentic stack is therefore not one project. It's not one framework or one model. It is a shared architecture built from open source software, open standards, and composable components. And that is the arc of today's workshop. We will examine 4 foundational layers of that stack: environments, models, reinforcement learning, and compute. Each talk addresses a different technical challenge, but they share a common principle. The future of AI should be modular rather than monolithic, interoperable rather than captive, and open to participation rather than controlled by permission. This is not simply a philosophical reference. It is an architectural, economic, and strategic requirement for a healthy AI ecosystem. So thank you for being here, and thank you for contributing to that future. With that, we will begin with our first speaker, Ben Burtonshaw. So Ben is from Hugging Face. Ben will introduce OpenEnv, an open standard and community hub for building, sharing, and running agentic environments. These environments define the tools, APIs, credentials, execution contexts, and tasks through which agents learn and operate. Ben will explain why shared environment specifications and harness protocols are essential for reproducible training, safer execution, and collaboration across the open source ecosystem. So with that, please welcome Ben to the stage.
Hi everyone, so as you heard, I'm Ben from Hugging Face, and I'm going to talk to you about a project called OpenEnv and open source agentic RL environments in general. My opinion, my hypothesis, is that RL environments are the best way to democratize AI, the best way to kind of take a stake in AI, mainly because they're pretty easy to build. They're just applications, they're just the kind of things that we do on a daily basis for that reason, and everyone can get involved. So I'll work through this in a pretty kind of high level and ecosystem kind of perspective, and then Daniel's going to kind of go even deeper on RL, and we're going to go quite far on it. But if I miss anything, please come and ask me questions afterwards or contact me. So what is an RL environment, right? The simplest way to explain what an RL environment is that it's a world that an actor acts within, or that an agent acts within. The kind of original RL environment would be a chess game, where the board is the world, the pieces are the state of the environment, the rules are the actions or the moves that you can make within the game, and the score, the game score, is the reward. And in reinforcement learning, we would use that reward to update our agent and to learn from that. So that's just a game, but let's kind of scale that up now to something a bit more realistic. So we could take software engineering. If we say that software engineering is defined as a task that's in a GitHub issue, and the work is in the GitHub pull request, and the score of that work are the results of the test suite and maybe the CI, then we would say that we have an environment that's there for software engineering. And this is how papers like Swee Smith and others have built software engineering environments. We could take this and we could then remove the work that from the pull request. We could remove the code from the pull request and get an agent to generate that code in that same environment and use that test suite to get our reward. And then we have an environment for software engineering that we could use to train a software engineering agent. Now, we could carry that archetype across many different tasks, right? Email triage or, say, project management. And we would need to find the tasks, the reward, and the state within those environments and build them into applications. And so this is what we're talking about with RL environments. OK, so what does the ecosystem look like? So to explain this, I kind of like to go back to something called the matter cycle. If you studied machine learning at school, you would have encountered it. It's the model, annotate, train, test, evaluate, revise loop. And it's not so common nowadays because it's a little bit outdated for modern machine learning, and we kind of need to update it a bit. So I like to update it to what I call a capability cycle. So if we look at a capability cycle, we would say that we discover capabilities, we then benchmark them, we represent them in data, and then we train models on them. Typically, we discover a capability with a harness or with some kind of prompt, right? We elicit this capability out of the model, and we can see that, OK, it is able to do a certain thing, maybe not reliably. We can then evaluate that capability, and we'll typically use another software stack for that, and we'll have an evaluation harness that will measure this capability in the model and how frequent, how reliable it is. And we can iterate upon that as a community. Next, we'll want to represent that as, firstly as a data set, and then eventually as an environment. And that's where domain expertise will come into this. And so companies like Merkle will do a great job of building reinforcement learning environments around capabilities for which they'll go out and speak to and hire domain experts in the respective domain and build that environment that encapsulates that capability, partially based on the benchmark, but ideally without any form of leakage between the two. And we'll then have a means that we can train a model on. And so that's when the trainers will come in, another part of the software stack, but also another community. Right now we'll have labs that are training models using these data sets and environments. So what you can see from this kind of capability cycle is that environments are the means with which that we move capabilities from domain experts into the models that we use. And once the models and harnesses have these abilities, then we kind of move on to the next one, and we know that, right, this capability is in the weights, as it were, right? OK, so that's a really high-level view. What you'll take from that cycle is that there are many moving parts, many different communities all playing in on the environment. And therefore, it's a really important part of the stack to be open, right? This is the means with which that we're communicating capabilities. Like, imagine if data sets were in a closed format. It would kind of be it would be a particularly horrible situation. And that's the goal of OpenEnv. So if you look for environments, you'll typically go to papers and GitHub, And you'll find that they're very distributed. If you look at the recent Kimi K3 paper, it came with thousands of environments. The Minimax paper had, I think, 10,000 environments. Even the first DeepSeek paper had roughly 1,000 environments. And all of these are implemented in different ways. Some of them are shared in different ways. Many of them are sold. And they're not something that's readily available in the way that open weight models are. It reminds me a lot of kind of being an MLE back in, say, 2017, when you would find weights, you would find implementations for models on GitHub, and then you'd go to Google Drive and you'd find the weights from there. And nothing is really exposed and interoperable in the way that it is today with model checkpoints. So that's the problem. And then that problem kind of compounds when you start to look at training. Daniel's going to go into this in more detail, but at a high level, a training process is a framework, right? We have a library like TRL or Unsloth that we use to update our model based on some kind of action that it does. And in this environment, we want to use, in this context, we want to use an agent harness to perform the task. So let's say it's the software engineering task. That agent harness is going to do that and interact with this environment, use tools in that environment, and then we're going to update the model. So at each of these edges, we have a different layer that needs to be interfaced, right? And we can't have a harness that expects a certain environment definition, and we need to also work with multiple harnesses like Pi and Codex and Claude Code, etc. So the challenge kind of compounds. One of the main mechanisms that we're working on in OpenEMS to get this to work are environment hubs. So on Hugging Face, we have about 4,000 environments now that can be pulled in a standard format that you can plug into most major training frameworks. There are other environment hubs like Prime Intellect, and there are also more coming, and we're collaborating with orgs to share our specs so that if they build environment hubs, they'll be able to use a spec such that they can download environments and share them in an easy way. So in code terms, like this is what it looks like to use OpenEMV. We imagine that it would mainly be driven by an agent, but it's a bit like Docker. So you'd say OpenEMV init, and you would get a scaffold of a kind of hello world environment that just gives you a generic score. And from that, you would just need to write the business logic for your environment, or you could generate the business logic with a code agent. You could also import environments from different libraries like verifiers, and then you can push, pull, and fork environments on the hub so that you can share them or use other people's and adapt them. That's the base layer of OpenEMV, and the features that we're working on next are to be able to discover environments from hubs and then to be able to validate them. So at the moment, the process of finding an environment for your use case is quite difficult. But if you could search for environments on the hub, you'd be able to pull those and get a range of community environments, which is quite nice. We can share with each other. And then that creates another challenge. How do I know which environment is better? How do I know which environment is going to help on my use case? And that's where this new validate command comes in, where we'll say, OK, this is a valid spec. And also, we can train a small model to see if it lifts performance on a given benchmark. So with these two commands, we'll have an autonomous loop for integrating environments in post-training. OK, so the last block of the talk is then how can I use an RL environment? So the quickest way to get started would be in evaluation. And I'd suggest that kind of most people do this because you can represent a typical workload as an environment, and you can see how good a model is. So you could take a model as weights or as just an API, and you could define your environment with a set of tasks and a reward function and run the model over those tasks, and you'd get back an aggregate score of how good a model is at your environment, right? The main way, or the core way that we would look at this would be with reinforcement learning. So we would take a model or a policy, and we would roll it out over this environment and get a set of actions. And then we would calculate rewards on each of those rollouts. We could use an algorithm like GRPO, which Daniel I know is going to come into further, where we would calculate the reward for each of those rollouts and then take a mean across the whole group and update the weights based on that mean. And then we'd iterate like that. So If you're interested in more detail on this, I've got a few talks where I go into greater detail on this, but at a high level, this is how we'd use an RL environment. And then the next way would be distillation. So in this setting, you wouldn't really be able to distill from strings, like you wouldn't be able to distill from tokens. You would need log probabilities. And we would take a student and a teacher model. We would roll out the student, so we'd get it to perform a task inside an environment, and we take the log probabilities of that student on this task. And then we would get a teacher to do the same task, or to roll out over the same token, and we take the log probabilities of the teacher on those tokens, and then update the weights of the student based on the difference, the reverse KL from the student and the teacher. That's one way. We could do this in a few different ways. So we could also take the student and do self-distillation, where we say, okay, let's take the best example of the student and compare it to the average. Or we could give the student some kind of privileged information or hint. We might get that from the environment or from a data set. Like, for example, in the pull request setup, we could say, here's the actual solution to this code, and we give that to the agent at the beginning, and then we update the weights based on the difference between its bad run and its good run. Okay, so that's the core of OpenEnv. That's what we're working on. The main takeaway is that we're trying to make it so that open environments can be shared openly across the Hugging Face Hub, but also others. And how do we think that this is going to work? How do we think it's going to be effective? The answer to that is leaderboards. Like we kind of see environments at the moment existing in a bit of a shadow realm. Like they're not really spoken about that much, or they're not really seen within the community around model releases. And we think that if people can start to build their own environments and try them out, and then we put them into leaderboards and we figure out which ones are good and which ones are contributing to model success, then more people will get involved and we'll share more of these leaderboards. So that's the talk.
Thanks, Ben. Thanks. Thanks. Hello. Thanks, Ben. Hello, is this working? All right, so there, it's actually working now, okay. So our next speaker is Daniel Han Chen, co-founder of Unsloth AI. Daniel's talk has a wonderful direct title, Making Open Models Not Suck. Open models are advancing rapidly, but anyone who's deployed them in an agentic system has encountered some practical problems for sure. Looping behavior, malformed tool calls, unreliable formatting, and failures that compound over long-running tasks. So Daniel will examine why these problems occur and what developers can do to make models more reliable, efficient, and genuinely competitive with closed systems. So with that, please welcome Daniel to the stage.
Hello. Hello? Oh, yes. Okay. Hello, everyone. Thanks for coming today. Yes, we have... Oh, wait. Okay, wait. Let me check. Oh, okay, there we go. Okay. It's a bit awkward, the computer, but okay, let's see if it works. If the slides, fail, please tell me. But yeah, hello, everyone. I'm Daniel from Unsloth, and great to be here. But today I'm going to be talking about how to make open models not fail, not suck, and how to make it much better overall. Yeah. So for you folks who don't know us, we're Unsloth. We are one of the largest organizations on Hugging Face, and we distribute models to the entire world. Okay, that number is outdated, but we have around 400 million total downloads on Hugging Face. We distribute the largest models and the smallest models, and we're the third largest distributor in the entire world. So we also don't just distribute models, so we also fix bugs and open source models. So we collaborate with all the large labs and hardware providers in the entire world to fix issues in the models before you get them. So if you're using open source models on your laptop, on your computers, they're most likely fixed by us in some way. For example, OpenAI's GPTOSS had some issues. Llama, Gemma, Mistral, all of these models have some issues. And we're here to help make the models much better for people to use. Recently, most people should know, Kimi K3 has been launched. It's the world's best open weight model that anyone can download. So they just released, you can download this on Hugging Face. It's quite large, 5 terabytes, but you can download this on Hugging Face. It was just released just a few days ago, Monday. And for what we did is we quantized it down to 1 bit for you to use. So it's not 1.5 terabytes anymore. It's around 600 GB. And Kimi K3 was actually 4-bit. So it's actually not that easy to quantize anymore because 4-bit going to 1-bit is not that much savings. But we show that you can retain 76 to 78% of accuracy, but you can reduce the size by 82%. So it doesn't, when you reduce the size of a model via quantization, you're not going to make the model 82% dumber. It's only like 16 or something % dumber. And we show, for example, some examples. A 1-bit Kimi did pretty well on some prompts. This is 1-bit, okay, versus the Kimi K3 at 4-bit, so the full precision, versus Claude, Opus, and GPT. DeepSeek just released an update yesterday. Was it yesterday? Yeah, I think it was yesterday. But yesterday they released 0731 for DeepSeek V4 Flash. So that was an interesting release at a weird time. And then they just randomly dropped it at some weird time zone. And so we also quantized it down for people to use. So you only need to use 90 GB of VRAM or RAM for you to run DeepSeek V4 Flash. And it is, I would say it's the best model for its size. So Kimi K3 is still much better, but it's ginormous. But DeepSeek V4 Flash can actually fit on your local computer and run it. So it works very, very well. So as open source models and closed source models, both of them are getting better and better over time. For folks, I'm not sure if you have seen the meter plot. So the meter plot shows the meter plot shows how much progress is there in AI. So for example, you can see Claude. The plot is a bit outdated because they have not updated it. But models can do tasks that take humans 16 hours to do, and it can do this very, very well. This is a 50% probability. So the 80% probability is a bit less. I think it's like 6 hours or so. But you can see models are progressing at an exponential speed. If you log it, so if you do a linear trend, you can see that the exponential progress is much more clear. I also plotted Mythos or Fable as the red line, and also GPT 5.6 Sol. So this actually removes cheating. So some of these models, they like to cheat. If you do include the cheating examples, then GPT 5.6 Sol is 270 hours. So if a human can do a task that takes 270 hours, GPT 5.6 Sol can also do it. However, that's probably not a good example. So if you remove all the cheating examples, it's around 16-ish hours. But you can see over time that models are improving at a dramatic pace. If you squint a little bit, there is actually this horizontal line area, right? So if you can see around 2023 to 2024-ish, there is actually a plateau approximately, if you can squint a little, right? So GPT-4 to GPT-4o, there was not that much progress. And the main reasoning behind this is because reinforcement learning and reasoning was not invented during that time. And so if you plot 2 different plots, like line plots, a trend, if you just plot the non-reasoning time frame versus the reasoning time frame, you can see that if we did not invent reasoning, so if O1 preview, if OpenAI did not tell everyone you can do reasoning, then AI models would have plateaued. And so if you can see the gray line, if you just plot, if you just fit a trend to the models before the reasoning age, all models would have plateaued by now. And the doubling time, so every single 7 months, the models will get double in capability. That was the olden days. But now the green trend is when you add reinforcement learning, you add reasoning, and you can see the doubling time has shrunk to 3.5 months. So this means you only need to wait 3.5 months for the model to be double in capability. So Opus 5 just got released a few days ago. Wait 3.5 months, and you will get an even better model than Opus 5. But remember, the trick is if the trend continues, right? So that's the fundamental question. Will the green line continue and continuously keep increasing for AI capability? Or we will go back in time and go to the gray line again, right? Will AI just slow down and and then we have to reinvent something new again? So this is a question that we will see in our lifetimes. So all you need to do is wait a few months and we shall see, right? So if you see models are plateauing, then this means AI has plateaued. So all you need to do is wait 3.5 months to 7 months, and we shall see the trend. So there is another very cool plot by artificial analysis. So they show open models versus closed source models. And you can see, so the blue line is open source models, and the black line is closed source models. And if you see very closely, open models have very, very closely reached closed source models. A better like indication, I'm not, my favorite gauge, if you want to like look at one benchmark, don't just look at SweBench or Deep Swe or whatever your favorite benchmark is. My favorite one is actually WeirdML. So if you search in Google WeirdML, this one is my favorite benchmark. And the reason why it's actually very hard to game. And you can see the blue line is open models, and the green line is closed models. According to WeirdML, Fable 5 is pretty good. It's very expensive, so I would suggest you to use Opus 5 High, which is, according to WeirdML, the best for its cost and accuracy. But for open models, Kimi-K3 is extremely powerful. You can see, for example, they also plot the accuracy across models. So Fable 5, okay, that has the highest accuracy and max reasoning, but it is very expensive. It's ginormously expensive. The next one is Opus 5 Max, Opus 5 High, and so on. And you can see Kimi-K3 is also on the leaderboard. So open models are definitely catching up. In fact, if you squint a little bit at the plot, this is a bit delayed. If you squint a little bit at the plot, there is actually the delay, as I was talking about, O1 preview and open models. And so this delay is what we call the open source drought, which was around 1.5 years ago. And in fact, if you take the closed source models minus the open models, you have this trend, which is the progress of open models. They're closing the gap. This line is a bit outdated, so it's more like 2 months delay. But you can see that with the invention of reinforcement learning and DeepSeek publishing how to do GRPO with DeepSeek R1, open models then again went back to trend. And so in fact, if DeepSeek R1 did not publish GRPO, open models would be 16 months behind closed source models. But now it's only 2 months behind. And there is this good blog post showing a trend extrapolation. By 2026 December, so in a few months, we shall get an open model that is as good as a closed source model. But this is all trends. So who knows if this is going to happen? All we need to do is wait a few months and we shall see. And so we shall see if open models can in fact be as good as a closed source model by December 2026. Another trend, I don't know if you guys saw, OpenAI decreased prices of GPT Luna by 80% a few days ago. This might sound very shocking, but actually it is not. And you can see on the Deep Swe, I don't know if folks use the Deep Swe benchmarks, but the Deep Swe benchmark shows that GPT 5.6 Luna is extremely, extremely efficient, cheap, and also very smart. And so the Deep Swe plot is to the right, to the top is the best. And so you can see GPT 5.6 Luna has dramatically shifted the line. And so the main question is, token prices are plummeting, but is this reasonable? People are thinking, okay, maybe OpenAI is just shedding all their money. Why can DeepSeek charge 10 cents versus other providers charging $1, right? Is this actually correct? So actually, I did a calculation before the talk. And so I don't know if you folks know semi-analysis. They released something called Inference X and benchmarks for VLLM, SGLang, and other inference engines on NVIDIA GPUs and AMD GPUs. And according to their benchmark, DeepSeek V4 Pro, so the biggest one, on one GPU, one B300, GB300, you can do 13K tokens throughput. If you calculate this, that means 1 hour you get 47 million tokens. If you saturate the GPU, 47 million tokens. Then, if you look at the price of GB300, it's around $5 per hour, approximately, per GPU, according to a semi-analysis, right? $5 approximately. And if you calculate this, right, you can do 47 million tokens per hour, $5 divided by that. That means that DeepSeek V4 Pro, the minimum floor price is 11 cents per 1 million tokens. And what does DeepSeek charge? DeepSeek charges 44 cents per 1 million tokens and 87 cents per 1 million tokens output. So this means that if you run DeepSeek V4, approximately, it's not a loss, right? It's not like OpenAI is shedding money or like DeepSeek is shedding money in terms of running these models. And that is why OpenAI can reduce the price of GPT 5.6 Luna to 20 cents and $1.20. And why? Assuming GPT 5.6 Luna is the same size as DeepSeek V4, okay, it's most likely not, but it's assuming it's the same size, then OpenAI still raises some money, around $1 per 1 million output. If you extract, also Kimi-K3, so Kimi-K3 is a new architecture. It's still not very optimized. But if you look at semi-analysis analysis, Kimi-K3 takes around 5K tokens throughput per GPU. So it's around 2.6 times less than DeepSeek. And if according to Kimi-K3, I don't know if you guys use the model, it is $15 per 1 million output. That is extremely expensive. And why? Because if you divide it, so it's actually 29 cents. The floor price for Kimi-K3 is 30 cents per 1 million tokens. So Kimi-K3 so Kimi, Moonshot, and the other inference providers are getting $14.70 on your API cost. So if they wanted to reduce price, they can, all the way to 30 cents. Obviously, well, you still need some revenue and some profit. So the price of these models are still slightly inflated, and DeepSeek is the only one which is charging, at close floor prices for their models. Another plot that I really like to look at is Arena. So Arena has this Pareto efficiency plot. Folks probably looked at Arena scores and stuff like this. I don't really like the Arena score, but the good way is to look at the Pareto efficiency plot that they publish. And you can see that, so to the top, to the right is always the best, as normal. But you can see there is a lot of models that are in this, Pareto efficiency line. And, for the performance that you want, you should look at which model you want to use. And so many open source models are also on the Pareto efficiency front. For web development, so if you want to do HTML development, web development, and stuff like that, Opus 5 Max for now is the best. However, Kimi-K3 is just behind it. So if you want to use a slightly cheaper model, and if you want to have still very good accuracy, Kimi-K3 is a very good model. GLM 5.2 is also on the plot, and other models. But if you don't want to pay API costs, there is another way. You can run the models locally on your computer, right? And the cost becomes zero, right? Not any cost, just electricity cost. Okay, some setup cost, some front-loaded cost. But yeah, essentially that is what we do. Essentially, we can reduce a model size to very, very small bits, like 1 bit, by using dynamic quantization. And we show many, many Twitter posts about this. We did it for GLM, we did it for Kimi, we did it for many, many, many other models. So if you go to our Hugging Face page, you can download these models that you can run locally on your computer. Some of them are very big. So Kimi is still 600 GB. So I'm not sure if that can run on your computer. But we're trying our best to reduce it to 1 bit, and even below 1 bit. How can we make Kimi 250 GB, for example? For example, a very good example is GLM 5.2, 1 bit. You can see this is one-shotted prompt. So we don't tell it to edit bugs or fix bugs and stuff like that. And you can see that GLM 5.2 does very, very well compared to the other closed source models. And remember, this is 1 bit versus full precision. So this is not some full precision model. We also show perplexity benchmarks to show you that 1 bit works well. KL divergence. So another way to benchmark these models is to use KL divergence. And yeah, so, oh wait, how much time do I have left? Or is that? Oh, okay. I shall skip this then. Okay, I will skip this. Okay, the last thing I'm going to talk about is Arc AGI. So folks, if a few days ago, OpenAI posted that in order to make models good, they showed that the Arc AGI benchmark is actually a bit bad for GPT. And the reason why is because they had a rolling truncation of 175K tokens. And they did not enable compaction. And they did not enable preserved thinking. And if you just enable these 2 flags, you can make OpenAI's models increase all the way to 40% accuracy. You don't need to do anything. Just enable compaction and do preserved thinking, and you will get high accuracy. And I was going to say other stuff oh, whatever. There's not enough time. We have some slides. I'll put some slides off. But yeah, thank you for listening, I guess. Yeah.
Thanks, Daniel. All right, so next up, we have Shang Yang from RadixArc introducing Miles, a flexible and scalable reinforcement learning framework for enterprise-facing agent training.
Okay, good afternoon, everyone. Thanks for the invitation. My name is Shang Yang, and I'm a research resident at RadixArc and a PhD student at MIT. So today, I'm very glad to introduce Miles to you guys on behalf of the team. And to begin with, Miles is a production-facing system for reinforcement learning from frontier language models with very fast speed and stability. And today we will first give you a very brief overview of the overall architecture of Miles, and then highlight some recent new release and new features of the Miles system. So let's dive in. And first of all, the first question is, what is Miles? And it is an open source RL engine for frontier models developed by RadiXArc. And the key point for Miles is that it's a stable, efficient, and reproducible reinforcement learning system at scale. So you can minimize the effort to run a reinforcement learning job on, the modern language models with different kind of environments and different kind of reward designs. So at a high level, there are 3 layers in Miles. First of all, we have SGLang as a reward engine, which is specialized for high throughput multi-turn generation, and it's also very compatible with nowadays agentic system, agentic environments, and agentic infra. And in the middle, we have the orchestration layer, which organizes everything like a reward engine and backend chaining systems as a whole, so you can make the RL system run very efficiently. And finally, we have support different kind of training engines, such as NVIDIA Maxon and FSDP. So it's also very flexible, and you can customize your own training engine on your own compute resource. And here are a key picture of the Miles architecture. So on the left, we have reward engine, which generate trajectories by interacting, for example, with the external environment. Or an agent framework, and the SGLang provides a generation layer. So while the environment itself can be very customized or alternated based on the customer's requirements. And in the middle, the system turns trajectories into some rewards, some loss functions, etc. So you have the training signals. And finally, we have as we mentioned, we have the Maxon or FSDP as the training backend. So you can update doing the forward and backward and compute the loss and update the model weights. And finally, these model weights will be synced back to the inference engines, the reward engine, so the whole pipeline can run in the circle. And why we use SGLang as a reward backend, there are some just some advantages. First of all, it's co-evolved with the RL workload, so including the partial reward support, and we can have dedicated reward control, so it's very easy to have your workload specified. And second, its router design is very high performance. For example, you can have a very well-designed cache aware load balancing for high throughput generation. And it also natively supports asynchronous generation with the training engine, which is a very important feature in nowadays reinforcement learning algorithms. And it's also fast-moving and there are a lot of optimizations. For example, SGLang supports speculative decoding with Miles, so you can use speculative decoding during the reward stage of reinforcement learning. And here are some key points that why Miles can change RL developers' workflow. So as we mentioned before, the first thing is that it's customizable. So we can support different kind of workloads just with some customizable function paths. So it can be very easy to define your own RL workloads and your own reward function and the update method. And it's also modularized and non-invasive. So it can be very easy to change to different training backends, for example, as we mentioned, FSDP and Maxon, and we will also support different kind of training backends in the near future. And here are some more technical details about the system design. So first of all, we have the reward engine, and we support multi-turn agentic reward, as we mentioned a lot of times before. And specifically, we support token in, token out, TITO for short, which means that we don't need to do the tokenize and detokenize again and again for the same multi-turn generation. So it can save a lot of cost and also makes the training more stable. And we also have R3 for MOE models, which means routing replay. So when training MOE models with RL, so you don't have to worry about the replay kind of things, which means that for different rounds you have different expert routed for the same for the same request, we don't want that, so we have the R3 to make sure that it's fully reproducible. And on the training side, we also support low precision RL, such as end-to-end MX FP8 support, and we also support per token NVIP4 quantization for the rollout stage, so that it can greatly decrease the training latency and increase the training throughput. And all these kind of things has been verified in our latest blog with the real-world training workloads. And we also have the LoRa support for resource-constrained scenarios, so that you can train large model with a smaller number of GPUs. And here is the current support metrics of the mouse. We recently launched the day zero support for newest models such as Kimi K3, the Inkling from Thinking Machines Lab, and we also support like DeepSeek V4, Nematron Ultra, etc. And we also have a wide range of precisions, as we mentioned, and also a wide range of hardwares. And more importantly, we support different kind of fine-tuning recipes, not only the SFT, RL, we also support OPD, on-policy distillation. And we have verified the mouse framework with over 1,000 GPUs for RL training workload, and we accelerate the RL training throughput. Like, for example, for Kimi K2.6, we can speed up the generation throughput to 12.5K output tokens per minute per GPU. And we also have optimized the stability, such as the R3 TITO, as we mentioned, and the precision aligned training, which help us to decrease the training inference mismatch. And we also support the fault tolerance recovery. And we support different kind of system, like the cluster backends, such as Rayon, Kubernetes, Slurm, and bare metal, etc. And finally, I'd like to mention some of our recent releases, like day zero support for Kimi K3, which is nearly a 3 trillion parameters model, and we do the fine-tuning with mouse on like different kind of tasks, such as the AMI math problem. So we, through the RL fine-tuning, we can increase the accuracy from 40-ish to 76%. And for the Inkling model from Thinking Machines Lab, which is also a 1 trillion level parameter model, we do the full parameter fine-tuning and the LoRa fine-tuning, and we also optimize the LoRa adapter synchronization, which means merge the LoRa rank into the SGLang inference engine. So this kind of things, we optimize it from almost 50 seconds to less than 3 seconds. And finally, we have a recent blog post about mixed precision training, as we mentioned before. So we verified that with different kind of precision choices, such as MX FP8 or NVIP4, we can maintain the model's accuracy and the stability during RL training, and we can also fundamentally accelerate the rollout speed and training speed by a great margin. Yeah, I think that's all about today's presentation. Thank you very much for the patience.
Thank you, Sheng. All right, our final speaker is Romain Bardouage from, he's a co-founder of SkyPilot. So Romain will make the case that AI needs an open compute layer. Please welcome Romain to the stage.
All right, there you go. Cool, thanks everyone. I'm Romeo, one of the co-founders of the SkyPilot project. And today, we heard really good talks about open environments, how to do RL in an open manner. I want to make the case that there's a need for an open compute layer for AI, and specifically something that sits between your workloads and the actual GPUs where your workloads run. So building AI infra is really hard, right? And let me walk you through it from OpenAI's perspective. Back in 2016, they signed an exclusive agreement with Azure to have Azure as the exclusive provider for the GPUs. But in 2024, they signed yet another deal with Oracle for $10 billion to get more compute. And only just a year later, they signed another $11 billion deal with CoreWeave to get even more GPUs, right? And even that's not enough. Like, you can see Sam Altman tweeting about, like, hey, we need more and more GPUs. Just give us a call if you can, like, secure more GPUs for us. So if the most capitalized company on the planet right now cannot secure enough GPUs, and if they're not able to get it in a single cluster, there's a good chance you also probably cannot do that right now. And so this GPU crunch is very, very real. And if you look at the typical AI organization today, typically you have an AI team, which has, say, some neo-cloud reservation. Maybe they signed like a 2-year or 3-year deal with one of the neo-clouds when hyperscalers didn't have capacity. Then they added some on-demand instances, maybe from the hyperscalers, just to supplement that capacity. But then they also end up having some kind of on-prem clusters, maybe for regulatory reasons, or they're just trying to keep data on-prem. And then you have customers in Europe, so you need to spin up clusters in Europe as well, so you need to maintain another cluster there. And then finally, you need a ton of CPUs to run your environments and sandboxes, and for that, you need to maintain another CPU cluster. So each of these is sort of a decision made at a point in time where it made sense to do that, but now you end up with this like big collection of clusters that you're now responsible for managing, right? And in some sense, reinforcement learning makes it worse, right? It makes it from, it makes it a scheduling problem, because if you think about reinforcement learning today, this whole thing is one job, but you can see it's composed of many subcomponents. So for example, you can see the trainer itself needs a lot of VRAM, needs many beefy GPUs, but at the same time, the rollout server, the one which is actually generating the trajectories, doesn't need as much VRAM, but needs a ton of them so that it can generate lots of trajectories. And then finally, to actually execute, for example, if you're doing like code generation models, your sandboxes need like a ton of CPUs in parallel to run all the trajectories, and you also need very fast cold starts on them. So the question then becomes like, why not just use existing solutions, right? Like cluster management has been, we've been doing it for a long time, so why not just use Slurm or Kubernetes, right? Slurm is pretty good. I mean, built 2 decades ago from the HPC world, and really, built for advanced scheduling capabilities, one of the best, I would say, quota and priority management systems out there. But it really doesn't support isolation in the form of containers. Yes, you can bolt on like Pyroot and more container layers on top of Slurm, but it wasn't really designed for it. And it wasn't really ever built for serving, so it was more for like batch jobs. Kubernetes, on the other hand, came on the scene about 10 years ago, really popular for microservices, and it's very, very elastic and sort of built for the cloud in some ways, but has like a super steep learning curve. Like if you hand Kubernetes to a researcher, they'll be like, how do I work with this? They'll probably just have to go to their agent to make it work. And it also doesn't have a lot of primitives that are needed for AI, specifically around like gang scheduling. Again, those are bolt on through like schedulers like Volcano and so on. But it's really hard to make Kubernetes work for AI. But more importantly, both are like single cluster matches. So they still don't solve the problem of like, hey, I have like 10 different clusters running. How do I manage them, right? So what's really missing is not a better scheduler, but something to manage all these different schedulers and platforms that you have today, right? So the goal is not to replace Kubernetes or Slurm. They're really good at what they do. But rather, you want to bridge this gap where you have some workloads like training, serving, sandboxes that you want to run on your compute, which is fragmented across like Kubernetes, Slurm, and so on. And so the idea is if we can have an open, unified compute layer, right, which can optimize availability, figure out what's the best place to run your jobs, handle their execution, and so on, and do this in a way where your workloads don't need to sort of know what's under the hood, that would add like a lot of value to the ecosystem. And that's exactly what we've been building at SkyPilot. It's a completely open source platform to use AI compute wherever you have it. And the idea is you bring your own framework, right? So you bring Ray, PyTorch, OpenEnv, Unsloth, your own frameworks, right? And then you submit them to SkyPilot saying that, hey, I need 8 B300s, for example, to run this job. And then SkyPilot takes care of the orchestration, right? It looks at your compute, your Slurm clusters, Kubernetes clusters, even cloud VMs, and then takes care of like orchestrating those resources, running the jobs, getting you the logs, results, et cetera. And SkyPilot started a few buildings away from here in the Soda Hall here at Berkeley. Open source, pretty active and healthy community of people using it and contributing to it. Also used by some of the biggest companies out there right now. And also, it's kind of rooted in the research we did back in the Sky Computing Lab. So just a really quick walkthrough of like what exactly is SkyPilot, how does it work? It's super simple. The simplest way to get some resources in SkyPilot is just to say, hey, Sky launch, provide what infra you want to run it on, and then state what GPUs you need. If I need to switch over from, say, Kubernetes to AWS, it's just like changing one flag. Similarly for GPUs, again, your application needs to be aware of what's running under the hood, but you can easily switch what GPU type is provisioned for you by just changing one flag. And then if you want to do more complex stuff, right, like not just provision some GPUs, but actually have a complex job, like a reinforcement learning run, we have this abstraction called job groups, where it's a declarative spec. So you say that, hey, I have a rollout server which needs these resources, needs to run these commands. Then I have to spin up, say, 1,000 sandboxes to run this stuff. I also need to, for example, have the rollout server running on H100s compared to the trainer, which may be running on B200s. And then it just passes over to SkyPilot, and then SkyPilot takes care of like the orchestration of this entire workload for you. And in doing so, it also provides some niceties. Like, for example, it'll provide you service discovery, lifecycle management. If one of the jobs fails, it doesn't mean the entire run needs to fail. It'll just like restart that job for you. Cool. So we've been talking about training, but serving is equally important. And serving also benefits from having a unified platform like this. Specifically, you gain capacity across all your clusters. So instead of having to launch, say, one K-serve instance in one cluster, you can have SkyPilot running inference across all your clusters. And when a failure happens, right, like SkyPilot can seamlessly move over your replicas to a region where you still have capacity. And one of the other benefits of sort of like having all your workloads run through one layer is that you can actually do very interesting stuff by running both inference and training together on the same compute, right? So the idea is you use the same GPUs, same giant cluster to run your jobs. But for example, if the inference requests start spiking up, SkyPilot can dynamically reallocate your resources from training to inference. So it preempts the training jobs. Your checkpointing logic takes care you don't lose data. And then when the inference spike dies out, it will automatically scale down inference again and then continue training. Cool. And I just want to reemphasize all of this is BYOC, right? So it's not like SkyPilot gets you, or like you don't give your credit card to SkyPilot to sort of like buy compute. You bring your own compute from your cloud provider, your own data. Everything runs on your own premises. So, I'll end here, but like really quickly, the idea is we don't need to reinvent, or like we don't need to replace Kubernetes or Slurm. They're really good at what they do. What we really need is a unified layer, which sort of like allows you to bridge the gap between your workloads and all those clusters that you're running. Cool. With that, I'll stop here. Thank you so much.
Thanks, Romo. All right, well, that does it for us today. Thank you, everybody, for hanging out, sweating it in the room here, and thanks for your support on open source.
I believe we have reception downstairs for those who are interested. Thank you, everyone.